Kiran sir.
Sir, good morning.
Good morning. Good morning.
और बताइए सर कैसे हैं? एक मिनट
आवाज सही आ रही है?
हाँ बिल्कुल सही आ रही है सर, आप बताइए।
कोई इको तो नहीं है ना?
नहीं सब सही है।
तो सरबजोत आ गई?
सर उन्हीं को फोन कर रहा था मैं, अभी बात नहीं हुई। आप देखेंगे क्या? फोन नहीं उठाया उसने। आ गई होगी वैसे तो। ठीक है, तो बस 10 मिनट बचे अभी। श्रीवास्तव सर भी नहीं आए।
थोड़ा सा बस वो देखना हमने वो टाइम शेड्यूल, क्योंकि सर का बिजी आ गए, बस ये देख लीजिएगा।
नहीं ठीक है, हम कोशिश करेंगे कि जल्दी से जैसे भी है शॉर्ट में करेंगे सर। बस श्रीवास्तव सर जुड़ जाए एक बार, मैं उनको भी फोन कर लेता हूँ।
हाँ उनको फोन कर लीजिए, मैं सरबजोत को देखता हूँ।
हाँ ठीक है। हेलो प्रवीण। Good morning, sir.
Hello. Hello.
Good morning, sir.
Morning, sir. Yes, sir. I'm ready. Let me know when to
Okay.
start. Yes.
No, your voice is breathing between.
Is it breaking, right?
Yeah, it was breaking.
Now it is fine.
Yeah, now it's fine.
Okay, sir.
Okay, so as Rohit sir told that, okay, we will start the program as per our schedule.
Yeah.
So I'm just waiting, I think. Just a moment.
Okay. So just let me know when director sir and registrar sir joins.
Hello, everyone. Good morning, everyone. There is, I want to share one information to all of you. We are facing some problem that today on this Google Meet, we cannot join more than 100 participants. So we have to remove some of the participants as the dignitaries and our director is going to join soon. So we are really sorry for this event. But for next session, we will try to change the platform if possible, where we can accommodate more participants directly. So I'm really sorry if I remove any students from this meeting right now. So please, you can join at our YouTube link. Thank you, and sorry for your inconvenience. Okay, so we have to remove some participants. सबको डिनाई करना है अभी ना, डिनाई करना सभी को. किसी को नहीं करना है.
किरण सर.
यस सर.
सर आप चाहे ना सिर्फ NITJ में रिस्ट्रिक्ट कर सकते हैं डोमेन को, एक बार आप चेक कर लो.
हाँ, NIT में
फिर आपसे अलाउ कर देना. लेकिन सर जो एक्सपर्ट्स हैं उनकी NIT की डोमेन नहीं होगी, वो भी ध्यान रखना होगा.
जी 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 सर. गुड मॉर्निंग सिन्हा सर. अभी डिनाई करना जो NIT के होंगे तुम करो, मैं इधर से और रिमूव करता हूँ, रिमूव करने पड़ेंगे.
गुड मॉर्निंग सर. सर आपका माइक ऑफ है. गुड मॉर्निंग सर. सिन्हा सर.
हाँ गुड मॉर्निंग. In fact, I had a meeting, so I have just finished my class and thought to see what is happening. Anyway, you just carry on. I'll have to leave now.
Okay, sir. Thank you very much to spare some time. I can understand that you have a busy schedule.
Okay. Thank you.
Thank you, sir. Thank you very much.
Thank you.
थैंक यू सर.
We have to remove the. रिमूव करो जल्दी जल्दी सबको, क्योंकि अगर रिमूव करना पड़ेंगे. नहीं, पास नहीं हो रहा. तो सर
किरण सर आपका माइक ऑन है, आप चाहे माइक तब तक म्यूट कर लीजिए.
मेरा सर गुड मॉर्निंग।
गुड मॉर्निंग सर, गुड मॉर्निंग।
सर टेक्निकल प्रॉब्लम है ये, वी कैन नॉट एक्सेप्ट मोर देन 100 पार्टिसिपेंट।
तो 2-4 डिलीट करके उनको ऐड कर लो।
हाँ वही कर रहे हैं, बाकी किसी को ऐड नहीं कर रहे हैं अभी।
नहीं ये क्यों हो रहा है ऐसा?
एक्चुअली पता नहीं सर, अभी तो एक्सप्लोर नहीं कर पाएंगे ये क्या हुआ ये पता नहीं। सो थोड़ी देर के लिए इनॉग्रेशन के लिए करते हैं कुछ पार्टिसिपेंट्स को रिमूव।
ठीक है, ठीक है। हाँ
Maybe, but Kiran sir, do not remove those people. I think you can request them to leave. Otherwise, they will not be able to join in ever again. That might be.
I don't think so. I think they can join again.
Good morning, sir.
Good morning.
Good morning, sir. Good morning.
अच्छा वो एक्चुअली ये लोग पॉलिसी चेंज की है यहाँ पे ना NIT जलंधर ने गूगल के साथ। आई थिंक मैक्सिमम हाँ, सो रिसेंटली दे हैव चेंज द पॉलिसी।
No, it was working well yesterday for other event, but I think from today onward they have changed. Maybe they announced it, but anyway, yeah, someone was saying something.
You just give a call to Bhupender, okay, if he can help in this regard, like okay, to allow।
मैं कर रहा हूँ किरण सर, मैं भूपिंदर को कॉल करता हूँ, आप अपना कंटिन्यू करिए इधर, कोई बात।
Okay sir, okay.
Good morning, sir.
Good morning, Dr. Sir. Good morning.
Good morning.
Good morning, Arvind sir.
Good morning, sir. Good morning.
Good morning, sir. Professor Van Srivastava is here. He joins. Very good morning, sir.
Good morning. Kindly be brief. If we can finish it in 10 minutes or 15 minutes.
Okay, sir. Good morning, sir. So, Sarabjot, please start the event.
Thank you.
किरण सर, सरबजोत को ज्वाइनिंग परमिशन दीजिए। सरबजोत को आपने ज्वाइन नहीं करवाया अभी, उसको परमिशन चाहिए ना।
अच्छा सर, उसको बोलो ज्वाइन करे प्लीज।
हाँ कर रही है।
आप लोगों ना
मेरा सर सरबजोत से बात हुई क्या?
स्विच ऑन कर लो आप और दोनों।
सरबजोत को यहीं बुला लो सर, यहाँ यहीं से कर दो।
सर आवाज आ रही है इसकी?
Sir,
Sarabjot, please start. Yes, you are, please.
okay, sir. As Robert Allen Silverstone says, we can create a more sustainable, cleaner, and safer world by making wiser energy choices. Believe me, coming to this energy sharing platform is one of the wisest choices you have made for the day. A bright, propitious morning to one and all. Reverend Director Sir, worthy Registrar Sir, distinguished Chief Guest, Professor Owen Srivastava Sir, esteemed faculty members, and all the curious souls who have joined us virtually. I, Sarabjot, on the behalf of Department of Physics at NITJ, extend a warm welcome to this TQ3 sponsored 5-day online short-term course on advanced energy materials. There is no energy crisis, only a crisis of ignorance. Ignorance of indiscriminate usage of oil and coal. Ignorance of the clean energy materials. Ignorance of efficient ways to tap Mother Nature's renewable gifts without compromising the environment. This e-course will echo the universal need to develop materials for energy generation, low energy processing, energy conservation and conversion to meet the increasing energy demand. It is a small effort to share latest development in multifarious ways to derive smart materials like supercapacitors, lithium sodium ion batteries, metal air batteries, solar cells, water splitting, etc. I invite the extremely energetic coordinator of the course, Dr. Kiran Singh, Assistant Professor, Department of Physics, to welcome the participants. So, am I audible?
Yes, sir. Yes, sir, Joe. Thank you very much.
Am I audible now?
Yes, sir, Joe.
Okay, maybe I lost the connection in between. Yeah, okay, sir. So I now invite extremely energetic coordinator of the course, Dr. Kiran Singh, Assistant Professor, Department of Physics, to welcome the participants and shed light on the details of the course. Sir, please.
Thank you, Sergio. A very warm good morning to everyone present here. I welcome to one and all present here for this inaugural ceremony of this 1 week short-term course on advanced energy materials. Warm greetings to all the dignitaries joining this event on Google Meet as well as live streaming at YouTube. We are really sorry that today on this Google Meet we can admit only 100 participants. As usual it was 250, but today there are some technical problems, so we are really sorry for that. It is a great pleasure and honor to be here today with Professor O.N. Srivastava, Padam Shri, Chief Guest of the event, Emeritus Professor at Banaras Hindu University, Banaras, Professor Lalit Kumar Avasthi, Director, NIT Jalandhar, Dr. H.K. Mishra, Registrar, NIT Jalandhar, Professor H.K. Sinha, Dean Research and Consultancy, Professor Agnihotri, Coordinator TQ3, Dr. Harlind Dhaiya, Head Department of Physics, faculty members of Department of Physics as well as other departments of NIT Jalandhar, all the dignitaries present online and dear participants. On behalf of the Department of Physics and organizing committee of this course, I welcome you all in this 1 week short-term course on advanced energy material during 12th to 16 October 2020. I will briefly discuss about the course. As we all know that the demand of energy increased enormously due to the advancement in the technology and modernization in last few decades. Hence, it is highly desirable to search for new renewable energy resources to fulfill the demand of green and clean energy. In this event, we focus to acquaint the participants to advanced energy materials. It is an interdisciplinary course and will be useful for all the branches of sciences and engineering. This course consists of 1 keynote lecture and 9 experts talk. This course is planned to cover different advanced energy material including hydrogen energy, photovoltaics, batteries, thermoelectric material, piezoelectrics, magnetoelectric devices, and capacitors. The response for this course is overwhelming, and within 5 days, more than 1,075 participants from different research and academic institutes have been registered for this course. The credit of this goes to the expert of this course who are well known nationally and internationally, and hence the participants would like to attend their experts' talk. We would like to mention here that for this course, not only participants from India, but we also have the participants, more than 30 participants from abroad, from different countries including Canada, France, Spain, Mexico, Cameroon, Philippines, Nigeria, Egypt, Nepal, Algeria, and Pakistan. We have distinguished speakers, Professor O.N. Srivastava, Professor Satish Ogle, Professor Rajiv Ranjan, Professor Sundaresan, Professor Kanishka Vishwas, Dr. Manjusha Silke, Dr. P.C. Pant, Professor Sagar Mitra, Professor Ranjit, Professor Chandra. So we are very much thankful to all of you all of our experts for accepting our request to be the part of this course. It is a great pleasure and honor for me to welcome Professor O.N. Srivastava, Padam Shri and Chief Guest of the course and keynote speaker of this event. Sir, your presence in this event is serious, encouraging, inspiring and motivational, not only for the participants, but also to all the faculty members of Department of Physics at NIT Jalandhar. Thank you very much, sir, for accepting our request to be here on this occasion. We are also very much thankful to Professor Lalit Kumar Avasthi, Director NIT Jalandhar, for inspiring and motivating us to organize such informative events at NIT Jalandhar. I would take the opportunity to mention here that NIT Jalandhar achieving new heights day by day under your visionary and dynamic leadership, sir. This year, NIT Jalandhar has achieved 52 position in NIRF ranking under your leadership, sir. NIT Jalandhar is continuously disseminating the knowledge even during this COVID-19 pandemic situation. We are proud to have a great mentor like you, sir. Thank you very much for your source all the time and present here in this inaugural ceremony also in spite of your busy schedule. Thanks to the internet and online platform due to which we are able to organize such events online during this situation. Thank you everyone. We are looking forward to have informative and knowledgeable week ahead. Thank you very much.
Thank you, sir. We want to fundamentally change the way the world uses energy. We want to change the entire energy infrastructure of the world to zero carbon. This is not just Elon Musk's dream, but every individual striving for a better tomorrow. I now invite the co-patron of the course, the lady of substance with an ever-radiating source of positive energy, our head of the department, Dr. Helene Daya, to familiarize everyone with the achievements of the department. Ma'am, please.
Thank you, Sarabjot. So good morning, everyone. I am very pleased to be here today to extend to you all a very hearty and warm welcome on behalf of the Department of Physics, NIT Jalandhar, for this e-short-term course. The Physics Department is committed towards high-quality teaching and excellence in research. We encourage innovation and research among the students through projects and developmental activities. Above all, we inculcate moral and ethical values with a sense of competitiveness, self-confidence, and sincerity among the students to make them a good human and a good citizen. I consider it a very special honor to welcome Professor Lalit Kumar Avasthi, Director, NITJ, who has been instrumental in taking NITJ amongst the highly ranked institutions. We are thankful to you for taking time and blessing us. Sir, we can never thank you in words for your far-sighted vision and support to NITJ. It is the result of his encouragement and persuasion that the faculty members have given their best performance in the last few years. This certainly has led to optimism and self-confidence in the faculty members, and they feel motivated enough to give more to the institute and to the society. We will always be indebted to you for your contribution to NITJ. We would like to extend a special welcome to our guest of honor, Professor O.N. Srivastava, who would be speaking shortly. He is a source of motivation for many researchers, and his contribution to science is enormous. I am so thankful to you for accepting our invitation and agreeing to deliver a talk. I am sure the young researchers will gain a lot. I also feel very happy to see so many colleagues and students. We are without a doubt especially grateful to you for joining us here today. So thank you all and wish you and the coordinators all the best. Hope you all gain a lot from the course and learn from the experts. Thank you.
Thank you, ma'am, for inspiring us every day. With due respect, I now invite our respected Director, Sir, Dr. L.K. Avasthi, to welcome our honorable guest and share his insurmountable wisdom with us. Sir, please.
Good morning. Greetings from NIT Jalandhar. Padam Shri, Shri O.N. Srivastava ji, the expert of the day, Dr. Harleen, Dr. Mehra, Dr. Kiran, faculty members, and all the participants for this online course. I, on my personal behalf and on behalf of NIT Jalandhar, extend a warm welcome to all of you. NIT Jalandhar, this institute came in 1987 as Regional Engineering College Jalandhar, and with a humble beginning of 100 students. Now we are an institute of national importance, a NIT, and we have undergraduate intake of 1135. We have started in between in 2006 many MTech courses, and recently 5 new MTech courses were added. Now total we have 16 MTech courses with a total intake of around 550 students. The institute usually takes 125 research scholars. This topic, the advanced energy materials, has been chosen very nicely. Energy, water, your air pollution, that way. These are going to be the things where we focus in the coming years, apart from artificial intelligence and machine learning, big data analytics on one side. So if we have to progress, we need to put a lot of effort in using the renewable energy resources. So there is much more than the N of the required energy which is dissipated by sun, but we are not able to have good storage, for which there is a gap between the demand and the supply. So if the research is progressed in this advanced energy material, and we are able to get some big breakthrough in materials which can help store this huge amount of energy, probably we will not be in deficit of any kind of energy. But definitely the galaxy of experts which you have chosen, they are going to give insight to the young researchers in the country. If our country need to progress, it is only on the wheels of research, progress in science and technology. And we can always become a developed nation based on these technical inputs. I hope NIT Jalandhar will be able to play its part for research in advanced energy materials and other pursuits, and hope that these deliberations will be useful for all the participants. Lastly, I hope that everyone connected and their near and dear ones, they are in good health during this pandemic time. Thank you. Jai Hind, Jai Bharat.
Thank you, sir, for blessing us with your motivating words and gracious presence. We make a living by what we get, but we make a life by what we give. I now invite Dr. Abhinav Pratap Singh, Assistant Professor, Coordinator of the course, and a man who personifies diligence, to present a formal vote of thanks. Sir, please.
Thank you, Sarabjot. Good morning, everyone. Welcome to the short-term course on advanced energy materials. The overwhelming response of the participants from India and abroad is a reflection on the relevance of the short-term course and the galaxy of speakers we have. I thank the experts, including Padma Shri Professor O.N. Srivastav, sir, the keynote speaker for the course, for accepting our request to spare some time of their busy schedule to share their wisdom with us. I thank all the participants for their encouragement through their enthusiastic response. Efforts to organize such courses cannot bear fruit without the encouragement from our institute authorities. I thank Professor L.K. Awasthi, Director NIT Jalandhar, for his constant encouragement for the academic activities and promoting the environment of learning even in such challenging times. Thank you, sir. We are lucky to have Dr. Harleen Dahiya as the head of the department. She has been working hard for the department ever since she took charge, which is evident from the progress made by the physics department. She has enthused the department with positivity and all-round activity. Thank you so much, ma'am. We thank the registrar, Dr. S.K. Mishra, for the administrative support for the academic activities. Thank you, sir. We will fail in our duties if I do not mention the backbone of this, and dare I say, all such activities of the department, our research scholars and MSc students. They take all the load of these activities off our shoulders with a smile. Without them, organizing such events may not be possible. Thank you. I thank all the faculty and staff members for their constant support and encouragement. Lastly, I would like to say that it is always a pleasure to work with Dr. Rohit Mehra and Dr. Kiran Singh. Their hard work and dedication motivates me. Thanks to both of you. Thank you everyone. Jai Hind.
Many thanks to you, sir, and Dr. Kiran Singh for successful planning of this knowledge platform. I thank you all for joining us for this inaugural session of ESTC on advanced energy materials. Now we'll start with the first expert lecture. On this auspicious day, I extend my heartfelt salutations to our chief guest, Professor O.N. Srivastava, and also the expert for the first lecture of the STC, the material physicist whose reputation precedes his work. He is currently Emeritus Professor of Banaras Hindu University and Vice President for India and South Asia of International Association for Hydrogen Energy. He secured his master's degree in physics in 1961 from BHU and followed it up with a doctoral degree from the same institution in 1966. After doing his postdoctoral research at Cornell University, USA, he returned to India as a lecturer at BHU, where he served in different capacities as that of a reader, professor, head of the Department of Physics, and coordinator of Center of Advanced Studies, Hydrogen Energy Center. With about 440 international research publications and 2 books in his academic crown, his research interests cater to carbon nanostructures, graphene, applications in hydrogen storage materials, nanomedicines, targeted drug delivery, hydrogen energy storage and applications in 2 or 3-wheelers fueled by hydrogen, quasi-crystalline materials, high-temperature superconductors, colossal magnetoresistance, and ferroic materials. He has undertaken several projects for various government agencies like DST and DRDO. He has been involved in organizing many social conferences and has mentored 57 doctoral students. He is a fellow of International Academy of Physical Sciences, fellow of New York Science Academy, and an elected fellow of International Association of Hydrogen Energy 2010. He is a humble recipient of innumerable awards and honors, prime being Shanti Swarup Bhatnagar Award for Physical Sciences in 1988, Goyal Award for Physical Sciences in 2000, Homi J. Bhabha Award in Applied Sciences 2002, ICMR Award on Superconductivity and Material Science 2010, and the Chief Padma Shri 2016. It is indeed a matter of great privilege to have such a decorated scientist amongst us. Without much delay, I now invite Professor O.N. Srivastava to bless us with his pearls of wisdom and the first talk of this ESTC titled Why Renewable Energy. Sir, please.
किरण सर अनम्यूट कर दीजिए आप।
हाँ जी सर।
डॉक्टर किरण उनको अनम्यूट करिए ना, पिन करके।
हो नहीं रहा सर, कर रहा हूँ। हाँ जी सर, हो गया। या इट्स ओके सर। नाउ
नहीं पड़ रहा है।
नहीं सर, सर आपकी आवाज आ रही है सर, स्क्रीन शेयर नहीं हुआ अभी।
नहीं होता।
yes, yes. It's good. Are you able to see?
Yes, sir. Fine, sir. Now it's okay.
Honorable Professor Awasthi, Director of the Institute, Dr. Kiran Singh, the Convener and Coordinator, Dr. Harleen Dahia, Head of Department, Dr. Rohit Mehta, Convener, Dr. A.P. Singh, Convener and Coordinator. I am very happy to be present on this occasion and give this lecture to you. I am at Banaras University, and these are two of my junior colleagues who joined with me on Harvard Center. And these are the research scholars who work under various kinds of projects. Now, energy is something which is fundamental to life. We can live without other things, but we cannot live without energy. Unlike other requirements, energy is required for the very sustenance of life and is required in increasing amounts as we increase efficiency of our working to add comfort. You see, there are two types of energy. One is provided by the nature, so the photosynthesis, the food that we have. So we have taken this carbohydrate version food, which is produced by photosynthesis by nature, and therefore we are able to work and our mind works. So this is the nature provided energy. Then to make life easier and increase the efficiency, we have several kinds of energy variants that we have discovered ourselves, like solar cells, like hydrogen, like wind, and so on and so forth. So these are some of the energies which we have produced for our comfort and to increase the efficiency. But this is the energy which is provided by nature. Remember that this energy has a very small efficiency, less than 1%. But still, because photosynthesis works at a very large scale, therefore this is successful. So this gives the hint that even if the system, renewable energy system has low efficiency, but if it works on a large scale for a country like India, it is worthwhile. Then at present we derive our energy mostly from the fossil fuels, that is electricity from coal and motive power like vehicular transport from petrol and oil. So this coal and petrol or oil are the fossil fuels which dominantly are in use by us. In this presentation, I will focus mostly on the oil or petroleum and its renewable replacement. Also, since this 1 week short-term course focuses on advanced energy materials, I have selected the use of nanomaterials. Because out of the various materials, use of nanomaterials in harnessing renewable energy, particularly hydrogen energy, is the one which I would like to focus. Now, what are the issues with fossil fuel? Because the fossil fuel is there in plenty of various types, but what are the issues which requires renewable energy, and what is the Indian situation regarding this? Now, this slide shows that what are the issues with the fossil fuels. For example, you see here that Delhi's winter crisis, when a lot of smog is there, and pollution, urban air pollution, for example, this Jagodh has the highest concentration of pollution in PM2 particulate matter 2.5. Then we have so many Allahabad, Gwalior, Patna, Kanpur, etc., so many cities of India. So this is one reason. The other reason is global warming, because the climate change is taking place, the earth is getting warm, and this is producing climate change. And this climate change is a very important thing which has come to forth recently. And as you can see, the glaciers are melting here.
So many of the cities like Dhaka, Calcutta, and Bombay will get submerged in 20 years' time. Then another important thing is that we have very small amount of world reserve oil or petroleum, which is very important. The quantity that we have is 0.9% only, which is very, very small. Therefore, we have to get most of the oil from outside, and this import costs us huge money. So therefore pollution, urban air pollution, climate change, and scarcity of oil or scarcity of petrol are some of the things which form the issues with the fossil fuel. This fossil fuel, which is petroleum or oil. Similar is the case with coal, but I will confine to oil or this thing in the present lecture. Then availability of oil. As you see, most of the oil is confined to Saudi Arabia, United States, Russia, etc., and we are down here, somewhere here. So the production of oil that we have is very small, and we have the second largest populated country in the world. Therefore, our position is very precarious. Then oil reserves. Oil reserve is also, as you see here, we are down here. So again, our position is very precarious. Now, China does not face the same problem because they have sufficient amount of oil available, and therefore they don't have to import too much of oil as we do. Now, in USA, for instance, the amount of oil which they produce indigenously, 8,905 million tons, and which they consume, which they use is something like twice. This is 8, this is 18. But in India, we produce only 894 million tons, but we consume 36. So 4 times more we consume than we produce. So our position is very different, and we need almost more than 90% of oil to be imported from outside. Now, problems which India faces is the global warming or the climate change, urban air pollution, as you know, then economic crisis. This economic crisis arises due to the fact that we import a lot of oil and this costs us huge amount of money. Present position. Oil import by India in 2018 was 229 million tons at $85 billion US. If prices are higher than $75 will be there, then you have to spend 100 billions of dollars. Oil import bill increases due to the increasing quantity of oil that we are supposed to produce because our energy requirements are increasing, and also due to devaluation of the rupee in comparison to. So in 2019, for which the full data is available, we imported 130 billion tons, and this was something like 9 lakh crores. So we spent 9 lakh crores of money to import oil from outside. This is a very huge amount, and this forms a very significant portion of the foreign exchange reserves that we have. Remember that when Chandrasekhar was the Prime Minister, we have to mortgage our gold from Reserve Bank of India to Bank of London to get sufficient amount of foreign exchange to get oil. Because if we don't have petroleum or oil, then our transport will stop and life will stop because we cannot move from one place to another. Most of the transport is through trucks or cars. Now, therefore, the problem is evident that we have an economic problem also associated with the continuous use of the fossil fuels. Then another type of oil has come into picture. This is shale oil. This is a recent one. This is found in the stones, and this can be taken out by putting hot water from one side, and then the shale oil comes on the outside. This is not as good as petroleum, but it can be made usable. Now, USA has a huge potential of $2.8 to $3.8 trillion of shale oil. Now, therefore, summing it up, what are the energy issues in India? 10 years back, we said that extremely small amount of oil reserves that we have is the most significant problem. Therefore, the largest difference between production and consumption. Consumption is 4 times more than what we produce. Unlike USA, where consumption is only twice as what they produce, then you have urban air pollution, and then it is global warming or the climate change. At present, this was about 10 years back. At present, global warming or climate change has become the top issue. Extremely scant oil is the second issue. Largest difference because of this extremely scant oil production, you have the largest difference between production and consumption of oil. and this pollution is there, but it has become the use of the CNG and so on. It has taken the last platform. So at present for India, climate change is top effect when issue with the fossil fuels. Of course, both petroleum and coal, because both of them produce CO2. And then extremely scant shows our population is increasing and we have to get more and more petroleum to be used. So largest difference between this and pollution. So these are the issues at present, the continuous use of the fossil fuels for India. Global warming, as I told you, has become very important. And why it has become very important, if one has to understand this issue briefly, when you try to find out what are the issues with the fossil fuels. Now you know that when the sunlight comes here, the CO2 blanket produced by burning coal and petroleum, and the solar light is able to pass through, and then it comes to Earth. When it comes to Earth, and Earth warms up, and it sends secondary radiation, these secondary radiation are not powerful enough. So they are not able to penetrate the CO2 and they return back to Earth. So when the secondary radiations from heated Earth return back to Earth, then Earth gets warmer and warmer, and this is the climate change effect. Now there is very good physics behind it. Sometimes people are not able to understand why Earth's temperature is increasing. Its phase is not warming. Earth has the atmospheric belt attached to it. Therefore, atmosphere may be the most likely reason for the warming of the Earth. Atmosphere has various gases, oxygen, nitrogen, and other gases. Then CO2, ozone, NOx, etc. Out of these, it turns out that CO2 is the culprit. CO2 is the gas which produces global warming. How it produces has certain amount of physics behind it, which was not clear earlier, but now it has become clear. It is like the following. This is CO2 molecule. So in the visible region, and ultraviolet, of course, very high energy, so it will get dissociated in carbon and oxygen. But in the visible region, where most of the radiation is confined, the CO2 can vibrate. So this vibrational energy of the CO2, the visible radiation, which has wavelength of 3,000 to let's say 6,000 angstroms, is able to excite the CO2 molecules. It will not be able to excite other molecules like O3, like NOx, like NO2, etc., etc. But CO2 is such that it is these visible photons are able to excite it, and this undergoes vibrations, and this, when it returns back, it emits energy. That is the heat energy, and these are the absorption bands produced from CO2. So because the CO2 structure is such, the binding energy of CO2 molecule is such that visible radiation is able to excite it, and then it absorbs this and gets excited, returns back to normal state and emits radiation. So you see, these are the CO2 molecules emitting radiation. They emit radiation in all directions, not only to the Earth, but that portion of the radiation which comes back to Earth produces global warming. So you see, there is a physics behind it that spectroscopy, let us say, CO2 molecules get excited by visible radiation, where most of solar photon energy is confined, and then they return back and emit radiation, and a part of that radiation which comes to Earth, something goes in the space also. But the one which comes to the Earth hits the Earth, and then from the secondary radiation emitted by the Earth are not able to cross the CO2 belt and return back to atmosphere. The solar arrives on the Earth, radiation sent back from Earth wavelength frequencies which can excite trigger vibrational modes of specific molecules, and this specific molecule is CO2. And when they return back to the ground state, they emit radiation, and this is the thermal radiation, this is the heat energy of thermal radiation which comes, and that is how the global warming effect is produced. Now, this is a picture taken from NASA, which says how the Earth has warmed from 1880 to 1884. It continues to in 1905, 1917. As you can see, this yellowish and reddish spots which are coming are the heating effects. And this is this picture is a reliable one produced by NASA, 2016. So this is up to 2016. So you see, as compared to previous, the Earth has got warmer. Here it is red portion shows that it has already warmed up significantly as compared to say 50 years back. Now, why climate change effects are very serious for India? It is not so serious for USA. It is not so serious for Europe or Russia, but it is so very serious for India. Why it is so? Why should we be looking for vigorously for a fuel which does not produce climate change effects? See, USA is a cold country. The rise of temperature, let us say by global warming of 2 degrees centigrade, does not actually affect us seriously. Actually, it helps them in the beginning because it's a very cold country. But we are a warm country, so a rise of 2 degrees centigrade is a hell of a thing for us, and it produces harmful effects. Change in monsoon pattern, then change in agricultural yield, which is very important. So unlike USA, India gets affected by this rise in temperature, global warming more seriously than this. Then they don't have Himalaya. We have Himalaya type of mountain. So glacier melting will affect India most crucially. Some of the cities will get drowned in the like Calcutta, Bombay, etc. Then use of green fuels, low carbon fuels like Jatropha, etc. is okay for them. But here it produces food versus fuel crisis. If we use our land to produce biofuels, then there is a problem that where will we produce food? Because we also need huge amount of food. But what is more important is this, that agricultural GDP in USA contributes only 0.9% to GDP. Here it produces very significant amount. It is GDP affects 20 to 23%. So agriculture is getting affected by global warming and this contributes significantly to our GDP. Therefore, unlike USA, climate change effect or global warming affects us more seriously. So what is there? We already have something like 430 ppm of CO2 and the maximum amount that can be tolerated is 450 ppm. So only there is a gap of 20 ppm. So this 20 ppm should not be produced because if this is produced, the temperature will rise more than 2 degrees centigrade. And in the global summit 2016, it was said that temperature must not rise more than 2 degrees centigrade in 2050. So by 2050, temperature must not increase by more than 2 degrees centigrade. This accord was signed by every country. Of course, the US President Trump has gone out of it. He doesn't believe in this. But all other countries, Europe, Russia, USA, China, India, etc., have solved it. I agreed to it and signed it. So the temperature, the global warming should be checked so that temperature does not increase above 2 degrees centigrade by 2050. If it increases, then 17% loss of agriculture is there due to this global warming or climate change effect. And India has decided that they will reduce this CO2 production, which produces global warming, by 33 to 35% by 2030. This is a signed document by India, the UNO, and the Global Climate Change Summit in Paris. India is already facing and will facing climate change effect more seriously. More electricity, more coal burning, then more CO2, looming threat of carbon tax, etc. If by 2050 temperature increases more than 2 degrees centigrade, then what will happen? The birds will start dying because they cannot suffer that kind of temperature rise, will die. If it increases more than 4 degrees centigrade, human beings will start getting affected. In other words, they will be the one who will start perishing. And this is a picture which shows that in Kerala, sometimes when the temperature became more than 49 degrees centigrade, many of the birds on the tree died and fell on the ground. There is already evidence that rise of temperature has very serious consequences for human beings, for agriculture, and for everything, and more seriously for India. Not so much for Russia and USA, cold countries in Europe, but very seriously for India. And this is again a picture where some of the animals have died. This is the fishes which have died. If by 2050 temperature should not increase by 2 degrees centigrade, and what fuel should we use? We are using, for example, petroleum, which has this red is hydrogen and this black is carbon. So it's a mixture of carbon and hydrogen. The ratio is 2:1. Coal, of course, is here. So we use coal to produce electricity. We use petroleum to run the vehicles and so on, run the airplanes. But all of them contain hydrogen and carbon. Only the ratio is different. Then LPG. LPG is the one which has less amount of carbon only 3 carbon and let us say 8 hydrogen. So LPG is slightly better than coal and this. CNG has only 1 carbon, so that is why CNG was used in Delhi, but it did not sustain very long because the number of vehicles kept on increasing. The use of CNG has not resulted in decrease of the urban air pollution. But what about this? Suppose I say, but I don't have any carbon, only hydrogen. So if carbon is removed and only hydrogen is there, so there is no carbon and no CO2 will be produced, no global warming or no climate change effect will produce. So that is why hydrogen is something, hydrogen is a fuel which has been used. For example, it is used in the rockets. The second is a rocket. And in Second World War also, when there was no petroleum left in Russia, hydrogen was used. But hydrogen is most useful for India in the sense that we have very small amount of petroleum oil, and also when we use hydrogen, there is no CO2 emission, there is no global warming, there will be no decrease in the agricultural yield, there will be no glacier melting, etc., etc. So for India, hydrogen is more useful than other countries. What is the energy vector which can take care of global warming and also address other issues? Now you see in the Vedas, it is written that the eventual inexhaustible and source of energy, clean source of energy, is the element which is common to both sun and ocean. What is the element common to sun and ocean? In sun is the hydrogen isotopes, deuterium and tritium, which fuse together, hydrogen, and what is there in ocean? H2O. So what is common between this and this is hydrogen. So in following Vedas, it was clear that the
Sir, श्रीवास्तव सर,
yes,
सर आपका प्रेजेंटेशन नहीं आ रहा है सर.
नहीं आ रहा है?
हाँ नहीं सर, शायद बंद हो गया प्रेजेंटेशन. हाँ सर, एक बार फिर से करें सर स्क्रीन शेयर.
कुछ नहीं आ रहा है कि अब आना बंद हो गया है?
सर अब आना बंद हुआ, पहले आ रहा था, सब कुछ ठीक था सर.
अच्छा. ठीक कर रहे हैं, अभी ठीक कर रहे हैं.
ठीक है सर, ठीक है.
Hello.
बंद हो गया है.
Dear participants, we are working to resolve this issue, so don't worry. Wait for a minute. ठीक है सर, ठीक है अभी
आ रहा है?
हाँ जी सर, थैंक यू सर।
Okay, so let me quickly say this, that thousands of years back it was predicted that the ultimate source of energy will be the element common to both sun and ocean, and hydrogen isotopes here combined together, and ocean has H2O, so hydrogen. Hundreds of years back, another one predicted that water will be the coal of the future. Water will replace coal and petroleum in the future. Now, what is there is that I can take water and use solar energy, for instance. I can use other energies as well, and split this hydrogen, split this water to become hydrogen oxygen. Then this hydrogen I can burn in scooter, I can run railway, I can run the airplane. And what is there is that after the use, this combines with atmospheric oxygen and produces steam and water. To produce from water, it burns back to water. So this is beauty of this, that suppose I take 1 liter of water and split it into hydrogen and oxygen, and then hydrogen is burned in the IC engine or fuel cell or in airplane and so on, and eventually it becomes steam and returns back to water. So produced from water, hydrogen burns back to water. It is thus indigenous, renewable, clean and climate friendly. India has tremendous water resources, Indian Ocean, Arabian Sea, Bay of Bengal. And also it has a significant amount of solar energy. Only next to South Africa, 120 watts per centimeter square or about 1.2 kilowatts per meter square. So only South Africa has higher energy, solar energy. So therefore, because of tremendous resources of water that we have, and also the very tremendous sun irradiation that we have, hydrogen is the one which is going to be very useful for the country. Now, why hydrogen for India? As I told you that now this global warming has become the top consideration, and of course pollution and other things. Now here I am trying to show one small video which shows like this, that these are the vehicles which are running on hydrogen. It is using hydrogen fuel, not the petrol or diesel or anything. And after this has run, these vehicles have run, then what is the byproduct? So you see the byproduct is this is the vehicle. So you can see that after the vehicle has run, what is coming out is water. So I have produced this hydrogen from water, and after running it returns back to water. Therefore, this is a very useful fuel that it is renewable. I mean, you use solar energy, but next day you have to again a fresh amount of solar energy. But here the water that you use is returned back. Now hydrogen is the eventual solution of the only carbon neutral fuel. There is no other fuel which does not contain carbon, and therefore it is the only fuel which will not produce global warming or climate change or urban air pollution, because these are produced from carbon and carbon derivatives. Then suppose we want to use hydrogen and try to show that this is very useful, then you have to worry about the production, how it is stored, because the director Awasthi was telling that the story is a small problem, the safety and the application. So I will now give some glimpses of the research that we do on these various aspects. Hydrogen, how hydrogen is produced, and how it is stored, and how it is, let us say, so there are various routes through which hydrogen can be produced. But the one which uses solar energy and water is the most common one, which is being thought of useful. There are some photosynthetic process and biohydrogen production, and coal can also be converted to hydrogen. So there is a variety of these things. And above all, there is a waste hydrogen or byproduct hydrogen which is produced by chlor-alkali industry. They don't need it, they throw it in the air. So Punjab Alkali produces millions of tons of hydrogen, because NaCl plus H2 is NaOH plus H2 plus Cl2. So this H2 and Cl2 they don't need, so they went off in the air, so that hydrogen can be taken and used as a fuel. Now this is a small setup in our laboratory that is a photovoltaic solar panel, as you see here. And this is converted to hydrogen. As you can see, this bubbling here is hydrogen. So solar photovoltaic is used to produce hydrogen. And this hydrogen is gets stored in some hydrogen. The process shows how hydrogen can be produced. This is the production of hydrogen in the laboratory. And as you see, there is a canister here, where it is stored in this hydrogen. This is the one where it is stored. So hydrogen can be produced from water in two ways. One of them is simple electrolysis. So electrolysis consists of two things. First, you produce electricity from photovoltaic panel, and then you electrolyze it. So efficiency of electrolysis, electrolyzing plant, and the efficiency of photovoltaic, and combined efficiency is about 9%. But I can use solar from photovoltaic panel. And what is the advantage is that you have to store solar energy. But here the hydrogen which is produced can be stored and used whenever you like. So this is on the anode you have this oxygen coming out, and on the cathode the hydrogen coming out. So there is simple electrolysis, and electricity can be obtained from photovoltaic. Then these are some of the papers that our students published in the last 5 years on hydrogen production. And as you can see here, that the voltage that you require, you take water. I mean, you take water here, and you make it conducting with water insulating, put some NaOH, and then apply electricity here, 1.23 volts. Then it splits into oxygen and hydrogen. Simple electrolysis. Then there is photoelectrolysis. Photoelectrolysis means that you don't use you use sun directly, and you split the water into OH plus H, and therefore, and then there's photocatalytic. You put some powder here. So these are solar photo-induced process, and this is simple electrolysis, and electricity can be produced by any source. So now, use of nanomaterials. Suppose I do electrolysis and use the conventional electrodes, steel electrodes, then I get hydrogen and oxygen. But suppose I use a nanomaterial like graphene. Suppose graphene is the electrode. Then what is the difference? It is shown in this. As I told you that I will demonstrate this use of nanomaterials, and these are advanced materials for use of production and storage of hydrogen. Suppose I have this photovoltaic panel, and this is the sun, and I produce this electricity, photovoltaic electricity, to carry out electrolysis. Then these are the steel electrodes that I have, and hydrogen is produced here, that, and oxygen is produced here. But if I use graphene as the electrode instead of this steel, suppose I use this graphene as the electrode anode, then I find that the rate of production of hydrogen is higher. As you can see, rate of production of hydrogen becomes higher as compared to conventional electrolysis using conventional electrodes. Here, one of the electrodes, the anode, is made of graphene, the carbon nanomaterial. It can also be carbon nanotube. It can be mixture of the two. So this is the demonstration. And what you see here, that as compared to usual electrodes, when you use the carbon nanotube, the rate of production is high. I can produce a composite material, graphene and carbon nanotube. So GC 64 means 60% graphene and 40% carbon. 60% graphene, 40% carbon. So I can produce this material by taking graphene and then sonicating it in water and then mixing it with the CNT, and therefore this is the composite material. These lines are CNT and this is graphene. So if I use this one, and this is the Raman spectra which shows that the composite material has been made, and as you can see, this carbon nanotube only, and this is graphene only. This is a mixture of this CNT, this is graphene. But if I make combined material, 60-40, 70-30, or 80-20, then you can see that CNT is piercing this graphene sheets, so it doesn't allow them to agglomerate. These are the CNTs which are crossing across this graphene sheet. Here it's only graphene sheet, here it's only CNT. So if I do that and produce this composite material, then I find that the rate of hydrogen production measured by the current for this 73 believe is the highest. 80% graphene, 20% CNT, 70% graphene, 30%. So this is so this 73 shows the maximum production of hydrogen. This one. This composite material tells us that how, if we take nanomaterials, then hydrogen production is going to be more efficient, and therefore the cost will go down. Why it happens? If you take FETIR spectra, then you find that when you use graphene or composite material, then there is a peak here. But if you don't use conventional electrodes, steel electrodes, then there is no peak. And this peak is the one which tells us let us say this OH radical. OH radical absorbed here on a graphene or carbon nanotube is because of the interaction here, it gets lengthened. This CNT radical like this, which is the conventional radical, if it is not carbon nanotube or graphene electrode, then this becomes, let us say, elongated like this, and then this length, increasing length makes it decut. As compared to here, OH are less energetically bounded here, and they are also a little bit curved. So I can break this easily to produce oxygen and hydrogen as compared to the one which is free OH. So that is the reason which happens, and therefore use of nanomaterials, graphene, carbon nanotube composite with G73 most efficient, and therefore we have, and this paper is published by one Dr. Patel, one of my students in 2018. Now, then photoelectrolysis. What happens in photoelectrolysis? In photoelectrolysis, you don't use separately electricity and then electrolyze. Both the things are done together. The H2O, solar photon react with H2O, holes react with H2O and produce half O2 plus H2, and hydrogen reacts with electrons and produces H2. So here oxygen and hydrogen are produced directly. You don't have to do electrolysis, photoelectrolysis. Solar radiation falling on this, and hydrogen is produced here, and this is produced here. This H2O reacts with the whole, makes oxygen and hydrogen, and this 2H combines with the electrons and go from here to photoelectrolysis. So we have done work on TiO2 graphene composite anode for solar hydrogen production. TiO2 is a well-known material which produces hydrogen, but very low efficiency, and if we make TiO2 graphene composite, so here it is shown. If you make TiO2, it is well known now that, for example, your toothpaste contains 70% TiO2. So you can take toothpaste and make TiO2 if you like, and then you make TiO2 with salt gel technique, and then you synthesize the graphene by the usual well-known standard Hammer or Hammer's method, and mix them too. So you have a geo-mixed TiO2 dispersion, and this can be. So this is the TiO2. This spherical things are TiO2. And this is graphene sheet, geo sheet, graphene oxide sheet. Now suppose I suspend them here, and then therefore I have TiO2, and then this graphene sheet, and then if I irradiate this with ultraviolet light, so this is ultraviolet light will emit electrons from TiO2, and these electrons, for instance here, this electron which is a small dot, will react with graphene oxide and reduce it. So by irradiating this composite only with the ultraviolet light produces reduced graphene sheet, which are much more efficient. So what is going to happen is that this is reduced graphene sheet TiO2 composite, and this Raman spectra confirms the presence of 150 in 2D band, that this is reduced graphene oxide. And here you see that this is reduced graphene oxide, this is TiO2, and therefore the electron transfer. What is major difference is that in the usual case, this electron travels like this and comes and diffuses, so it has a chance of recombination with the whole. But when you have graphene with TiO2, then graphene scavenges these electrons and they come directly like this. This works like a ladder, and this electron which is produced from solar radiation, I am showing only the electrons, not the holes. So this electron will find light on this graphene sheet and come here, and will not have a chance to recombine. But whereas here, in the usual case, only TiO2, so graphene oxide, reduced graphene and TiO2 makes a much better electrode. And the rate of production of hydrogen, as you see here, with this curve here, is much higher as compared to conventional one. What it means is that if I take TiO2, the well-known material which produces hydrogen with low efficiency, and couple this with graphene oxide, reduced graphene oxide, then I have very good hydrogen production efficiency. Then the other thing is storage. As I told you that storage is the other thing which is important. Why? Because hydrogen is very light. It is 16 times lighter than air. So if you produce hydrogen, it will leak in the air. It will, by buoyancy effect, it will go in the atmosphere. So you have to somehow capture it and store it. So how to store it? There are various, for example, in the battery, in the mobile, you put a battery here, and this battery, let us say, is the one which stores it and goes inside and sits here somewhere here. Similarly here I have a hydrate tank here which has hydrogen soaked into it. and this tank is put in the vehicle, goes here and sits in the back of it. This hydrogen, which is in this hydride, solid state hydride stored there, works like the fuel tank. And since this is hydrogen, it burns with atmospheric oxygen, produces steam and water, and no CO2, no global warming, no air pollution. And this is indigenous fuel because I have water, I have solar radiation, so I don't have to get anything from outside. These are some of the papers of our students which do on storage of hydrogen by various techniques. There are three very important storage modes. There are many, but three: high pressure gaseous, storage in liquid hydrogen, which is used in the space rockets, storage in intermetallic hydride, solid state storage. So it turns out that hydrogen storage in solids, they are more efficient, they are safest mode, they generally satisfy the requirement which storage is used. Why they are more efficient? Because suppose this is a hydrogen gas or liquid, so it is stored in the form of the molecule, which occupies a lot of space. But in solid, what happens? The hydrogen molecule breaks into hydrogen atoms, and the atoms go and sit inside. So as you can see, the density of hydrogen storage here is much higher than here. More number of hydrogen per unit area, per unit volume is stored here. So solid state storage on the hydrides are better storage systems. Also, it is not there. Unless I change the pressure and change the temperature, they will not come out. Whereas here, if there is a leak, they will go out and burn. In ISC Bangalore, there was an explosion with hydrogen gas because they were using gaseous hydrogen. So as compared to gaseous, this is more safe because they are locked inside hydrogen. They only after a change of pressure, temperature, they will come out. And this is the one where a small leak, even if there is a leak in the tank, nothing will happen because hydrogen cannot come out on its own. But here it can come out on its own, combined with oxygen and explode. So safest. And the requirement is that there should be 30 kilogram per meter square to compete with petroleum and 6 weight percent. So as you can see, if I use a gaseous storage system, which is a three-wheeler, so I will have to use a very big volume here. So this is risky because a leak will lead to explosion. And also, the volume wise is not useful because it is much bigger than the vehicle itself. Therefore, and another thing is that if I use the high pressure gases, liquid hydrogen storage, then if there is explosion, it will explode like this. On the other hand, if I use the hydride solid state storage system, where hydrogen is soaked inside a solid, then I will have this solid tank put here. So if there is an accident, this tank with hydrogen will leak and go in the air because it's lighted there, and nothing happens to the whole of the vehicle. Therefore, this is much more safer. Now, instead of telling many things that we have done, I will only confine to, let us say, one issue, which is glimpses of R&D done at VHU and hydrogen storage. So, for instance, this is NGH2. NGH2 is very useful. Magnesium hydride is a very useful storage material because it stores 7.6 weight percent of hydrogen and volume-wise 120 kilogram per meter cube. This is much more than the required quantities which are there for competing with petroleum or oil. Even 6 weight percent is good enough to compete with oil. It is already 7.6. 80 kilogram per meter cube is ready, there to, we can compete with oil or petroleum, but it is 120. So this is a better storage system than petroleum. And of course, burning will produce H2O. So this is hydrogen and this is magnesium. So magnesium hydride. So what I need is that temperature is here, high desorption temperature, 400 degrees centigrade there, and the kinetics is sluggish, much less amount of hydrogen comes out. These two things have to be brought in control by research. And what we do is that we use some catalysts. So suppose I use this catalyst here. These catalysts can help break this bond of hydrogen and magnesium, and hydrogen will come out. And again, I can put the reverse process, I can put this back. So I have to find new catalysts. I have to find new catalysts to sends electrons. Electrons disturb this bond and hydrogen is broken. So this research has been done at BHU, quite a bit of it. And one of the materials that we have used is this caustic crystalline alloy, aluminum, copper, iron. And this is aluminum, copper, iron. We remove this aluminum by etching it with acid. So you have, let us say, this is aluminum which is removed, and only copper and iron are there. And what is interesting is that this is the absorption curve. I take this LCOFE aluminum removed from the LCOFE. So hydrogen which is absorbed within less than a minute, this is minute here. So in less than a minute, you can see it is absorbed about 5.5 or 6% better than petroleum. More than petroleum. 6% within less than a minute, it is absorbed. And then at 150, that was like this. So therefore, significant amount of hydrogen gets absorbed in magnesium. And these are desorption curves. So when you heat it or change the pressure, then hydrogen is released. And then you can use it. And when it becomes empty, then again you charge it. So desorption kinetics of MgH2 is very good. These are some micrographs with color mapping, which shows how LCOFE and aluminum is removed and how hydrogen is located inside. So we are able to know the presence of the elements with the color mapping, some micrographs. I think you are familiar with this. And this is the model that I removed this aluminum here, and the aluminum atoms are removed, and only copper and iron are there, and they work as a catalyst. They help to achieve very good absorption and desorption, and therefore this is MgH2 is a viable hydride material. In other words, storage material. As I told you, storage has to be done because hydrogen is very light. It will escape in the air. They have to be stored. If you store in high pressure gases, it's very explosive and efficiency is low because molecules are stored. If you absorb in solid, then efficiency is very high because it is atoms which are go inside and absorb. And also it is locked inside. You change the temperature and pressure, only then it will come out and go in the engine or the fuel cell to be used. So these are the conclusions of this research. This one of research that how MgH2, with the help of the catalyst LCFE, MgH2 can be used as a storage material. There is another material, another system which has been used, and that is FeCO4 as the catalyst for MgH2. And this is the TiO2 quantum dots. As you can see here, these are TiO2 quantum dots. Quantum dots are special nanoparticles where size is comparable to the Bose radius. So these are the quantum dots of TiO2, and these are used as a catalyst for MgH2. And again, you do these analysis and you find that good absorption and desorption takes place. There are various types of catalysts that have been developed at BHU. And you see that with repeated use, the capacity doesn't increase significantly. It remains around 6.0. So we continue to use thousands of cycles, take out, put in, take out, put in. When you take out, hydrogen is burnt in the engine or fuel cell. And when it becomes empty, again charged with hydrogen, which is produced from solar energy or from some other source. The conclusion is that there are a variety of nanomaterials like LCFE, and TiO2 quantum dot, which can be used to take out and put in hydrogen in Mg. In other words, making it MgH2, again Mg, again MgH2, again Mg, like this. Take the hydrogen out and use in the engine or the fuel cell, and when it becomes Mg, then again charge it with hydrogen and so on. Now, finally, since I have consumed a sufficient amount of time, let me try to briefly tell about applications. So suppose I am able to produce hydrogen by using nanomaterials which show higher efficiency than the conventional materials, like TiO2 conventional material shows much less efficiency, but if TiO2 is made in the nano form, and similarly graphene is used as electrode for electrolysis, or fused graphene oxide and TiO2 is used for photoelectrolysis, then hydrogen is produced much more efficiently and the cost will go down. Now, how and safety-wise, if you store in the solid state, it is very safe. Then applications. I must demonstrate some applications. Use of hydrogen, for instance, in replacement of, let us say, petroleum. Because petroleum burn will produce CO2. Very small amount of petroleum is present in India, so we have to import more than 90% from outside. It produces global warming, climate change, all these problems. But if I use hydrogen, if I am able to do applications with hydrogen, then hydrogen can be produced. We have tremendous amount of water resources. Then we have solar radiation of 100 watts per centimeter square, which is only slightly less than Africa, but much more than Russia, USA, UK, and anywhere else. So we have water resources, we have solar radiation, and we have other ways of producing. So we can produce hydrogen stored in the solids so that they are safe. And now, as regards this application, you have to fabricate certain tanks, aluminum hollow tubes, to put the hydride inside. And as you can see, this is a tank here where the hollow tube of this, because thermal conductivity of hydride is poor, so the mass has to be distributed. The aluminum is very conductor, so the exhaust of the engine can come and hit this aluminum tube. And inside the aluminum is hydride powder. The hydride powder will start liberating hydrogen. The hydrogen will go in the system, and then the vehicle will run. One can do these calculations to find out the design of the, I will not go in detail, but design of the tank for pressing this hydrogen. This is aluminum tube. Inside you have these tubes, and this powder is there. Exhaust gas from the vehicle comes here, hot gases, and hits it. So hydrogen starts coming out from these tubes, and when they become empty, all the hydrogen will be used to charge them again. The injector which has been fabricated. So this is hydrogen induction. This is the way it is induced. For example, in the compression stroke, this hydrogen plus air mixture which is there, and in the expansion stroke, this comes out, this spark plug, and then here in the exhaust stroke, what comes out is water vapor. So I started with hydrogen, and in the exhaust, it is already basically it is CO2, NOx, and other things which will come out, produce global warming and all these things. But here it will, what will come out after the engine has run is water vapor, which will become water after getting condensed. Therefore, another thing is that people may say that why you are using this hydrogen for running the vehicle, and maybe I will run airplane and train and so on, many other things. But what about this, that can I produce electricity? Because I produce electricity from coal. So that coal also produces CO2 and therefore global warming. It turns out that very recently, 2 years back, powerhouses have been made where instead of burning coal, you burn hydrogen. If you burn coal and to produce electricity, then you produce CO2. But if you use hydrogen to run the turbine, burn hydrogen to produce heat and therefore steam, then you don't produce CO2. Burn hydrogen to run the turbine and to produce electricity. And the first electrical power station with hydrogen has been made. What is the advantage? The advantage is that I am using hydrogen, which I can produce myself. And then I am not producing global warming because hydrogen burning is producing only steam. So hydrogen power plant are replacing this coal-fired power plant will produce electricity. Already this has been developed in Italy, not in India at this time, but in Italy it has been developed recently, 2 years back. Another point is that nowadays people tell about battery. So whether battery is more useful for running vehicles. So is hydrogen required 4 kilograms to run 400 kilometers. And battery is 400 kilometers, charging time is 4 hours. And after 4 hours again you have to charge for 4 hours. Suppose I want to go from here, Varanasi to Lucknow, then I have to charge it again. This is a big drawback of the battery. One of my students which has gone to Netherlands has purchased a car of battery first. Then he says that to travel 100 kilometers, he has to devote 2 hours and then another 2 hours to charge it. But here it only takes 2 minutes. As I have told you, in hydrogen, less than a minute it gets charged. So in battery, you have to devote too much time for charging it after you have traveled to 100 kilometers. But here you travel to 400 kilometers and 400 kilometers you can easily run. Here you will take 8 hours to travel the same distance, where the hydrogen will take only 4 hours. The one advantage. Then another thing is that in battery you charge with electricity. So if you charge with electricity, then this is not going to stop the global warming because electricity is coming from the coal-fired power station. Only for such countries which do not burn coal, for example, Iceland and Canada, only for those countries battery is going to be useful. Otherwise, in India, to use battery, you will have to charge it like mobile, and charging means huge amount of electricity required, which will produce by thermal power station because 95% of electricity is produced in India by coal. Then air transport. Air transport is not possible with the, let us say, with the petroleum or kerosene which present is used because the weight. because the weight of the battery itself will be higher than the weight of the 26000 kilogram, which is higher than the weight of the Airbus, the plane itself. Whereas in hydrogen, Tupolev and Canberra and Boeing have used planes running on hydrogen. And recently, the train has been made. So to run a train, railway train by battery is going to be very difficult because again the weight of the battery will be too large. But here, a train has been made based on hydrogen. So you see, hydrogen is more viable fuel than battery, and you can have many advantages from this. Now, finally, I will try to show some of the devices that we have developed. For instance, cooking. Cooking can be done with hydrogen fuel, and this is a home cooker, so replacement of LPG. So this hydrogen you can make yourself at the rooftop of your building by using a solar panel, and you see this cooking is done here. Same way as LPG, but with the added advantage that I have produced this fuel myself. LPG has to be brought from outside, from Iran, Iraq, etc. And then I have, let us say, this vehicle. This is from Chidambaram, who there is a small car running on hydrogen, nano car, in which hydrogen will travel from Chidambaram, this one will government of India till 2019 will be there. And this is lady, and this is a three-wheeler running on hydrogen. So I will try to show this car. Hydrogen car. We were trying to make a huge, large number, say 10 three-wheelers run on hydrogen in Varanasi, so that it can be demonstrated that there is a fuel which we can produce ourselves. We don't have to import it from outside. There is a fuel which is clean in the sense that it doesn't produce urban air pollution, carbon and carbon variants, and also it doesn't produce global warming because CO2 is the culprit, and with hydrogen no CO2 is produced. So I had started with this. My time is going to be up. So why renewables? Why renewables are important? Because I told you that in India, with oil, there is a great problem. There is very small amount of reserve that we have. So we have to get more than 90%. So much so that at one time we have to mortgage our gold from Reserve Bank to get foreign exchange. Even now, if $1 increase in oil prices, then there is a 30,000 increase in budget. And most of the foreign exchange deposit reserves gets exhausted by purchasing petrol. 6 lakh crores, 1,000 crores is used. And then the other thing is that it produces urban air pollution and global warming. Global warming or climate change is the most serious effect at the moment for consideration for our country and other countries, because the fact that it affects our agriculture and among other things, and agriculture is the major contributor to our GDP. So therefore, how hydrogen is the best one that I told you that it is indigenous, it can be produced. And recently, Planning Commission, which is Niti Ayog, held a meeting on 23rd February 2020 this year to find out how hydrogen can be brought in India. And Japan has declared that in Olympics, which is of course postponed, they will use only hydrogen fuel things and no other petrol or diesel operated vehicles. Japan is particularly interested in bringing in hydrogen because, like us, they don't also have oil. Next country which is more interested are European Union, due to the fact that they are saying that global warming will affect them very seriously. America at the present time is not interested because Trump has refused to, although Obama signed the Paris Declaration, but Trump has gone out of it. But even then, many people in Baikal believe that this fossil fuels will be discarded slowly and slowly, and new renewable fuels will be brought in. Thank you very much for this kind attention. And if there are any questions, I will be happy to answer, or you can write to email to me and I will reply to you. Thank you.
Sarabjot.
Thank you, sir. Thank you so much for your enlightening talk. I'm sure the researchers all over the globe are inspired and will work out positively in this area. I now open the session for questions. And Dr. Kiran, take over.
Thank you, sir. Thank you very much for this informative talks. And I am sure that all the participants will get benefit from your expertise in this area. Sir, there are a few questions. I will ask. One question is, in covalent hydride, in which form hydrogen is present?
Hydrogen is present in atomic form. Hydrogen molecule breaks into hydrogen atoms at the surface of the solid, because the solid generally contains a metallic component. So at that metallic component, hydrogen molecule breaks into hydrogen atoms. Atoms go and sit inside at the vacant places called interstitials in the solid. So they are weakly bonded there. So they will not come out on their own. To take them out to put in the engine or to put in the fuel cell, you have to either change the pressure or heat it a little bit. So the exhaust heat of the engine can be circulated in the hydride tank, so that the hydride powder gets heated to 60 to 70 degrees, and then hydrogen starts coming out, and that is fed to the engine or fuel cell to produce the power. So in the form, in solid, hydrogen is stored in the form of atoms, not in the form of molecules. Whereas in gaseous and liquid form of storage, hydrogen is stored in the form of molecules.
Thank you, sir. Sir, there is one more question. What is the current market value of hydrogen fuel in India?
As I told you that about 60,000 tons of hydrogen is free. For example, as I told you, alkali, Punjab alkalis are here, Kanodia chemicals, all such industries which produce caustic soda for soap and other things. They use, let us say, salt, NaCl plus H2O. So NaOH, they form powder which they use, but NaCl plus H2O is NaOH, alkali plus H2 plus Cl2. So this H2 and Cl2, which comes in the form of a gas, is vented off in the air. So that H2 is of no use to them. So that H2 government perhaps can take or one can purchase. So that cost is only nominal. As regards the production from solar energy, if the efficiency is more than 10%, then it is going to be cheaper than petroleum, corresponding petroleum. At the present times, it is about 1.8 times costlier than petrol. But if the price of petrol becomes 80 per liter, then it competes with hydrogen. And already petroleum prices have increased. Earlier, 10 years back, they were about 50 rupees. Now it is 80 rupees per liter. So therefore, they are comparable at the present time to petroleum. In other words, I can run a vehicle on hydrogen and spend the same amount of money. The added advantage that this hydrogen I have somehow made in India itself, and also it is not producing urban air pollution, it is also not producing climate change effect, because the eventual byproduct is steam or water, no CO2. Hello?
Thank you very much, sir. Sir, there is one more question related to the cost constraints of hydrogen cell, sir. So one participant answer.
You see, it is like this, that there is a techno-economic calculation of the cost. So it has been found out that if you use, suppose I purchase a two-wheeler which runs on hydrogen. So the initial cost will be 15,000 more. Suppose the cost of the three-wheeler is 70,000 rupees, then it will become 85,000. But within 2.5 years, that extra cost will be repaid because the hydrogen fuel that we will use will be cheaper at the present time than petroleum. So after 2.5 years, the extra cost of rupees 15,000 is paid back. So after that, I am running on a fuel which is cheaper than petroleum. So there is a non-recurring cost of hydride tank and other things in the beginning. So the vehicle will cost 15,000 more for like a two-wheeler, but it gets paid back in the sense that the fuel that I am using, let us say the cost of the fuel is 60 rupees equivalent per liter, whereas petroleum is 80 rupees. Therefore, this 20 will get paid. So at the present time, when petrol was cheaper, it was 50 rupees, then hydrogen was costlier. But at the present time, when the cost of petroleum is 80 rupees per liter, hydrogen is no longer costlier, it's comparable or cheaper.
Thank you very much, sir. So now we will take only one and two short questions. Sir, somebody is asking, Arvind is asking that, okay, what about the safety? Is it safe to use hydrogen as a fuel? I think you have already demonstrated in the three-wheelers, cooking, etc. I think so. We will skip this question.
I told you that if there is an accident with a car, then petroleum is spreads on the ground and the whole car gets burned. But if it is an accident with the hydrogen one, the hydride tank which is put in the luggage carrier, there will be accident, then hydrogen will leak in the air because hydrogen is lighter than air, so it will go up. It will not spread on the floor. So as compared to petroleum, which in accident will, like in a plane, when there is an accident, the petroleum or the kerosene which is put in the airplane spreads on the ground and the whole plane burns. But if it was a hydrogen fueled airplane, then only that place where hydrogen is placed, in the accident, the hydrogen will go up, will not spread on the floor, and therefore the localized damage will be there, but the whole of the vehicle will not be burned. So it is safe. And from safety point of view, the storage in solid state form is the best. In gaseous form, it is risky. Suppose there is a gaseous tank of 200 atmosphere, so if there is a leak in the gaseous system, hydrogen will come out, will mix in the atmospheric air, and there may be explosion. But if it is in the form of a hydride, in other words, it is just like a sponge, water is absorbed in the sponge, and when you squeeze it, then water comes out. So similarly, solids absorb hydrogen, and they will come out only when you apply pressure difference or apply temperature difference. And this temperature can be applied by flowing the exhaust gas, which is steam, in the hydride tank itself. So instead of venting the exhaust in the air, you let the exhaust, which is at high temperature, get flown in the tank, so the hydride tank gets heated up, it starts emitting hydrogen. Therefore, it is self-sustained cycle. You don't have to heat from outside. The exhaust gas itself can heat the hydride tank. So when you use in the form of storage in the form of hydride, then it is very, very safe. If you use in the form of gas, then there is a chance of explosion, and there was an explosion in IISc Bangalore in January 2019, and some people died because they were not knowing, and they opened a hydrogen tank and something went wrong, so hydrogen came outside. It mixed with the atmospheric air, and there was some heat source or heater somewhere around in the lab, and the whole thing burned and exploded. So it is for domestic use and for use in the vehicles, it is also advisable to use hydrogen hydride solid state storage system where the hydrogen is absorbed in the solid and remains inside unless you take them out by heating, let us say like that. But in a gaseous one, you don't have to, a leak itself will let the hydrogen come out and mix with the atmospheric air readily. So using hydrogen in the form of high pressure gaseous is risky, but using hydrogen in a solid state hydride stored form is not risky, has been proved to be safe, and we have been doing this work for more than 8 years. And there is no explosion in our laboratory and no danger.
Thank you, sir. Sir, I will ask the last question now. What are the metal and alloys you are using for fabrication process for hydrogen storage?
At the present time, we use magnesium on one hand, and then sodium NaAlH4. Sodium aluminate NaAlH4 is the one, and NBS2 is the second, and the third is Mg2Ni, magnesium nickel. So we use about 23 different alloys, but we found that the three which are most potential are MgS2, and there is another system which is called metallic organic framework, MOF system. That organic framework systems are the ones where there is a metal atom like iron inside the cage, and that cage is made of carbon. The metallic organic framework on one hand, magnesium on the other, and the third is sodium aluminum, NaL. So these three systems which are light and which are useful. And for instance, magnesium is the fifth most abundant element. It is found on the sea water and also in the form of magnesium chloride. And on the earth, it is found in magnesium carbonate. So magnesium is very plentiful. Similarly, sodium is also very plentiful. Aluminum is plentiful. So we have selected such metals which can be found in huge quantities and which are available on earth, so that if you use a metal which is very scarce like titanium, then there is going to be difficulty. So the ones which use, and very recently we started using carbon nanomaterials, carbon aerogels. So carbon is a part of nature, oxygen, nitrogen, carbon. So carbon aerogel, graphene, and these materials, they absorb hydrogen under certain conditions. So these are going to be more useful than metal ones, because metal ones have limited stock anyway. Although aluminum, magnesium have huge stocks. But if you use such materials which are part of nature, like carbon in various forms, like graphene, punctualized graphene, then carbon nanotube, punctualized carbon nanotube, and particularly carbon aerogels, then it's a porous material, carbon aerogel. Then these carbon materials are going to be the next generation materials in the sense that they are inexhaustible, they are form of nature, and nature cycle keeps on producing carbon, nitrogen, oxygen, etc.
Thank you, sir. I was supposed to end, but there is one question. So there is a question that which is more efficient and beneficial, hydrogen storage devices or supercapacitor?
No, supercapacitor are different kinds of things. Supercapacitor is store electricity. Supercapacitor, for example, has a high, let us say, you can compare battery with supercapacitor. The battery has more power, but the rate of power delivery in supercapacitor is large. So you can run a car with a battery, but you cannot run a car with supercapacitor at the present time, because it will run only few, let us say, half a kilometer or something. So supercapacitors are devices which can store electricity. Hydrogen is a device which works for motive power. Motive power means the power which produces, like for instance, airplanes, railway trains, as I told you, then two-wheelers, three-wheelers, four-wheelers, etc., etc. All such places where oil or petroleum is being used presently can be replaced with hydrogen easily. Hydrogen can also produce electricity, as I told you that instead of coal, if you burn hydrogen in a turbine, recently they have started doing it. One power station has been made in Italy only, not in India. So therefore, supercapacitors are a storage system, highly efficient storage system for electrical power. In other words, if you produce electricity by photovoltaic power and you want to store it, so one way maybe that you use supercapacitor, charge it, and whenever required, you discharge to get the power. So you store solar energy, photovoltaic solar energy, or electricity in supercapacitor and use it whenever required. Suppose you want to run a special electrical device like a washing machine or like a, let's say, computer or other things, then battery and supercapacitors are useful as storage systems for electricity, not for petroleum. I mean, you cannot run, as I told you cannot run an airplane based on battery or supercapacitor, because the weight will be so heavy that they will be larger than the weight of the airplane itself. Whereas kerosene, which is the fuel for airplane at the present time, refined kerosene, has very little weight. But if you use hydrogen to run the airplane, then that is even lighter than kerosene. And when kerosene is used to run the airplane, you produce CO2, lot of CO2, so global warming. But when you use hydrogen, as I told you, there are some experiments done in the last 5 years by Boeing and propelling in Russia, running plane on hydrogen, not on kerosene. So you have a motive power which is being produced, and there the battery or capacitor in plane will not work because of the weight consideration. Another thing is that, for example, lithium-ion battery is the one which is most efficient, but lithium and the cobalt have very small deposits in Congo and Venezuela and so on. So the amount of lithium which is available is not enough to fuel even 50% of the cars of the world. Whereas hydrogen is something which you can produce in any amount, and when it burns, then it returns back to water. So if I use 1 billion cubic meter of water to produce hydrogen, then after I have used it, that 1 million ton returns back to me. But the same is not true with coal, or the same is not true with other kind of, if I burn kerosene, run the airplane, then what I get is CO2 and other gases. I don't get the kerosene back. But if I use hydrogen, then the amount of hydrogen in the battery does not change. As I have shown you that when the vehicle runs, the byproduct is the water itself, because the hydrogen burns with the atmospheric oxygen, produces steam, which condenses, becomes water. And this hydrogen I had produced in the beginning from water itself. So water produced from water, it burns back to water. It is completely renewable. This kind of property is not there in kerosene or petrol or coal. And supercapacitors and batteries are good storage devices for electricity. So, for example, a mobile will be very useful for getting charge from the battery. It will be difficult to use hydrogen there. But suppose I want to run a car, so I will, if I use hydrogen, then I don't produce urban air pollution, I don't produce climate change. We have to help the country because the amount of petroleum or oil that we have is very small, and we have to get it from outside. So we have to spend the foreign exchange. So therefore, supercapacitor has its own application. But at present time, hydrogen is much better for Indian condition as compared to supercapacitor. Very good systems for R&D and for laboratory with publishing research papers, etc. Lithium-ion batteries are also very good. And storage of solar energy is the one which is there for supercapacitor and batteries. In one case, the energy is high. In the other case, power is high. In batteries, energy is high. In supercapacitor, power is high. Both are different types of devices, but both store electricity and not the motive power.
Thank you, sir. Thank you very much for this informative talk. And we are very happy to have your presence on this occasion, sir. Thank you so much, sir. Thank you very much. It's really a great moment for Department of Physics at NIT Jalandhar that you have joined this event, sir. Thank you, sir. Thank you very much.
With this, we come to the end of the first session of the course on advanced energy materials. The Department of Physics.
Sarjot sir is saying something. Just wait.
Yes,
yes, sir, please. Hani sir, Srivastava sir.
Yes.
Sir, we are very much thankful to you, sir, to present here on this occasion. We thanks you again. Thank you very much, sir.
Okay, thank you.
I request all the participants to stay tuned for the upcoming afternoon session at 3 p.m. Also, do not forget to fill the Google form for feedback and attendance. The Department of Physics at NITJ is highly indebted to Professor O.N. Srivastava sir for serving the food of knowledge to all the inquisitive minds. Thank you for being with us.
Thank you, sir. Namaskar. Photo. Sir, we will meet sometime in person, sir. It's long time to meet you, sir.
Not shared.
So thank you very much. So we will leave the meeting now, and we will meet at 3 o'clock. We are really sorry for the inconvenience you faced, or some other participants who are watching us on YouTube due to this Google Meet, because today we can accommodate only 100 participants. So we are really sorry for that, and we are looking forward to have the solution to add more participants on our Google Meet or Microsoft Teams. So we will update you about that. Thank you very much. So now I will close the meeting. Thank you very much.
Thank you, sir. Thank you very much.
Good afternoon, sir. Shall I start?
Yes, let me ask Manju ma'am. Silke ma'am, are you there?
Yes, hi Kiran, I'm here.
Hi ma'am. Very good afternoon.
Good afternoon.
How are you ma'am? How are the things there?
I'm good. How are you?
We are also fine ma'am.
Hello,
Hi,
ma'am.
Harleen. Good to see you after 5 years.
Yeah, exactly 5 years.
Yes, I'm very happy that you have become head of this division.
No,
When I
accounting is just, in rotation. Otherwise, we are just all faculty here.
yeah, I'm sure. But
Okay, Manju ma'am, actually, Harleen ma'am told me that, okay, you met in US.
yes,
So
yes,
very nice to know me that, okay, you know each other.
yes. Yeah, I am also pleasantly surprised to see her name.
I was telling him that we had spent a very good time. We were together. It was a very fantastic meeting.
Yes, it was indeed you, and then the other people. I think a lot of people were there at that time. So we had really good time.
Yeah, so good to see you.
Yes, same here.
So, ma'am, let us start.
Yes, Kiran. Yeah.
Sarvjot, please.
Okay, thank you, sir. A happy afternoon to all the participants connected with us on this virtual knowledge platform. I, Sarabjot, extend a warm welcome to the noon session of second day of ESTC on Advanced Energy Materials 2020. I hope your stomachs are full, but I'm sure the brains are yearning for more. To quench our knowledge thirst, we are honored to have a highly decorated physicist, an epitome of women's strength, Dr. Manjusha V. Shelke, Principal Scientist, National Chemical Laboratory, Pune, amongst us. Dr. Shelke pursued her PhD from Advanced Materials and Processes Research Institute, CSIR, AMPRI, Bhopal, MP, from 2001 to 6, and postdoc from IIRI, IEMN, CNRS, France, 2007-8, with scholarship awarded by Embassy of France in India. She has been working as a scientist in Physical and Materials Chemistry Division, National Chemical Laboratory, Pune, since 2008. She was IUSSTF Visiting Researcher, Department of Material Science and Nanoengineering, Rice University, USA in 2013-14. Fellow of Maharashtra Academy of Sciences 2018, Kavli Fellow of National Academy of Sciences USA 2015 are amongst the numerous awards and honors bestowed upon her. She is a materials chemist, and her research interests cater to development of high-energy electrode materials for storage devices like rechargeable batteries and supercapacitors. Her group is extensively working on energy storage solutions for e-mobility and has published more than 60 high-impact journal publications in this area, with 4 patents granted. 10 of her students graduated with PhD in area of materials for energy storage. I, on the behalf of entire Department of Physics at NITJ, extend a cordial welcome to Dr. Shelke and I request her to bless us with the knowledge on lithium batteries. Ma'am, please.
Thank you. Thanks a lot. I also thank Kiran for inviting me to deliver talk in this short-term course on advanced energy materials. I know that NIT is one of the premier technology institute, especially NIT Jalandhar. I see in your course brochure also that it is ranking at 12th number among NITs, right? So, my talk is also about technology's favorite child of the moment, that is lithium-ion batteries. And I hope that you all had a good lunch, and I hope that you will not sleep during my talk. I'll try to make it more entertaining to you and more easy to understand, so that you will not get bored or you will not get, you will not sleep. Okay, fine. Yeah. So, in the morning, you have heard a very illuminating talk by an eminent personality like Professor Srivastava.
he was talking about fuel cells and how fuel cells can power the electric mobility and all. I could see the talk intermittently because there was quite disturbance, but in the end he has made a comparison between fuel cells and batteries, which is all over world. See, a lot of people are working on fuel cells and batteries, and those who are working on fuel cells, they say that fuel cell is the best technology for EVs. Those who do research on batteries, they say that batteries is the best technology for EVs. Well, I think such kind of comparison is not that, I must say is not correct, because both the technologies have some advantages and some disadvantages. And I believe that whichever technology becomes more viable, commercially viable to bring this clean energy storage in reality, that is good for us, that is good for our planet also. But at the moment, the most energy efficient technology is batteries, because batteries can give nearly 80% energy efficiency in electric vehicles, whereas fuel cells have only 20 to 25% energy efficiency. Of course, fuel cells have very large energy density, and the fuel hydrogen as a fuel is very lightweight. So the range of the EV can also be much higher than batteries. But as I say that there are some advantages and disadvantages. So, but I do work on batteries, and specifically batteries for EVs and also for stationary applications. So here I am. I'll tell you some broad basics of lithium-ion batteries, and then how they are being used in electric mobility. And then I'll tell you about working principles of current commercial lithium-ion batteries, their constructions, types, terminology used for lithium-ion batteries, and also about the materials that goes in lithium-ion batteries. Of course, because materials have always played an important role in human civilization and in realizing the technological advancements as well. Almost all the technological advances are influenced by functional and structural materials, and we know that the effect of functional materials on the society is tremendous, right? You are being able to listen to my talk while sitting in your home, or I am being able to talk to you while sitting in my home. It is because of the technological advancements, and advanced materials are the play their large role in realizing all these advancements, right? So to set the flow of my talk, I'll show you one picture. This is the Fifth Avenue, street called Fifth Avenue in New York City. So this picture was taken in the 1900 in the morning. You can see that the entire street is full of the horse-driven cars. There is hardly an automobile anywhere. And within 13 years, this is the same street of Fifth Avenue in New York City. So all the horse car driven vehicles are replaced by propel engine vehicles, right? So you can see how fast the technology progresses, and that is because of the engineering and the science and the materials research that goes behind all these advancements, right? Now we see there are a lot of types of vehicles and different technologies and are coming in the market, and all these vehicle manufacturers are bringing in new features to make our driving experience more pleasant and more comfortable, right? So you can see like a lot of fancy cars are there all around us. So but every technology has a bright side and a dark side, right? So if this is the bright side of a technology, then this is the dark side of the same technology. We live in India, so I need not to tell you how these vehicles or transportation is creating pollution and how it is damaging our planet. And that's why worldwide there is a call for like making clean energy or renewable energy and clean energy storage more viable, and everywhere the efforts are going on. Even in India also, the government of India under National Electric Mission has mandated complete electrification of public transport by 2030. So the mandate is to make most of the passenger cars or public transports like metros or maybe the buses, public buses and all based on electric mobility. So as of now, like commercially viable EVs are based on batteries. Of course, fuel cell is progressing a lot, and maybe in a decade or a couple of decades, maybe fuel cell will become more viable for mobility. But as of now, whatever current state of art is there, then batteries are more energy efficient. So how electric mobility can counter this climate change or this pollution issue, because this data is quite old. This is from 2009, but it shows us, it gives us the idea that 20% of global primary energy use is because of transportation, and whatever carbon dioxide emissions are there, energy related carbon dioxide emissions, 25% are there because of transportation, and nearly half of them are due to passenger vehicles. So if EVs can become more, you can say that affordable for the commoners, then it can drastically change the climate issue or the clean energy issue of the country. So how batteries are powering these EVs, that is what I'll show you during the course of my talk. But before that, I just want to briefly introduce you how batteries are invented. That is a very interesting story. So I really want you to tell that story about the invention of batteries. How many of you know the battery, or what battery? Do you have any idea about, like, I can't see the chats, but maybe you can just speak up in your mic if you know what battery means.
मैम अभी टेस्ला ने कुछ नया बैटरी के लिए इन्वेंशन किया है.
हाँ. No, I am asking you what is basic. What does it mean by that? Is different thing that Tesla has done.
Cells, a group of cells is a battery, and in this case, like in the picture you've shown, you have an anode and a cathode. So it's basically two electrodes immersed in an electrolyte solution.
Yes, that's right. So basically, battery is essentially a device that stores chemical energy that is converted into electricity. So they are kind of small chemical reactors with the reaction producing energetic electrons, which are ready to flow through the external device. But how all this started, that story I want to tell you. So this all started with the discovery of so-called animal electricity. Okay, so this story is quite freak. It was in 17th century when United States had just declared the independence, and France was rapidly heading towards bloody revolution. That was also the time when Britishers made inroads in our beloved country. So that was the kind of era when some really outstanding people were doing science experiments, and they have made really outstanding discoveries. So in this case also, an obscure Italian physiologist has done a science experiment. So in his back garden, he has installed a lightning rod. Okay, and that it was a time when there was a stormy night, and then he has put a lightning rod and he kept a dead frog on the table, and then he made a connection of frog's legs to the lightning rod. Okay, so when the storm came and lightning flashed nearby, the energy coursed down the rod and the frog's leg twitched. So that is quite filmy, right? An Italian scientist doing an experiment on dead frog and discovers that the body is powered by electrical impulses. So this scientist was Louis Galvani, and he has concluded that the body is powered by electrical impulses, and that's why frog's legs is twitching. This was quite interesting experiment at that time. And it has sent a shockwaves not only to the researchers across the disciplines like medicine and biology and physics, but also to the society. So several people got curious about this experiment, and some other scientists also started working on this experiment. There was another Italian scientist. His name was Alessandro Volta. He was a professor of physics. So he felt so inspired by this animal electricity experiment that he himself also tried to do this. But as many as experiments he has done, he has gradually become concerned that one of the Galvani's experiment had led to a false conclusion. So in this experiment, Galvani had connected frog's legs to its spinal cord using two different pieces of metals. So usually these metals are like iron and bronze, or iron and silver. And upon touching the metal to complete the circuit, the frog's leg was twitching. So what Volta thought that probably a frog is not playing any role here, and it is simply the metals that are creating this current. What Galvani concluded that electricity is intrinsic to the frog and metals are acting as a conduit. But Volta identified a flaw in Galvani's logic. And then he tried with different metals. So whether if electric current can be generated. So he tried to touch silver with copper and he found that electric current is there. Iron touching zinc, electric current is there. So with this evidence, Volta has argued that it is only the metals to different metals that is creating an electric current, and frog is not playing any role here. So bimetal electricity has left no room for intrinsic animal electricity. So Volta described how contact between dissimilar metal can create electric current. He also made a grand new invention based on this principle of bimetallic electricity that is called as voltaic pile. Okay, so this voltaic pile is better known as today as a battery, what we call as a battery. So Volta created a circuit with two different metals separated by a piece of cloth or cardboard soaked in a brine solution. So brine solution is an electrolyte here. And then completed circuit produce an electric current. And then he has stacked this element, the pair of copper and zinc discs and an electrolyte between them on the top of each other. So by doing that, he can adjust the amount of electricity produced to the desired level. So at that time, voltaic pile was a kind of revolutionary discovery. With this device, scientists could create a steady source of electricity for the first time, and harnessing electricity has become very simple, and that has a direct influence on the advances in chemistry, physics, and physiology. So this invention has proved to be one of the most important and impactful invention in the history. And as a testament of that impact, the standard unit of electric potential still bears Volta's name. The volt. We all know that electric potential has a unit, volt, right? So what happened to Galvani? Well, he died poor and obscure, unfortunately. No matter how flawed his experiment was, his hypothesis was not entirely wrong. Today we know that he catalyzed change in medical and physical sciences, and it has created another branch of medical science, which is called as neurophysics. It was indeed, the neurophysics has indeed based on a principle that bodies is having electrical impulses, right? So he didn't know, but his experiment has really made a lot of advancements in science. And these type of cells, electrochemical cells, are also called as galvanic cells or voltaic cells. So Galvani's story is a story of interactions, metals and frogs and scientists and other scientists, geopolitics, science and people's imagination, and a lot of things. Well, all these complex interactions gave rise to an incredible array of new ideas and understanding of body's electrical signaling, or entirely new field of study, that is batteries. Over the years, then several advances are made in this field and different chemistries were proposed and commercialized. So I'm not going to go into details of each and every chemistry, but I'm just highlighting two of them that are relevant to automotives. So almost all of our cars have lead acid batteries for starting, lighting, and ignition. You can see here that lead acid battery was discovered in 1859, right? So this is oldest type of rechargeable battery. And years later, Sony has commercialized the first lithium-ion battery, and the credit for this invention largely goes to the invention of the lithium cobalt oxide based battery to Professor John Goodenough. He was a solid state physicist from US. And then for that invention, I'm sure that you must be, I don't know, he got it. He was a physicist, but he got a Nobel Prize in chemistry last year. So these three gentlemen were responsible for making the lithium ion batteries commercially viable. So you can see now lithium ion batteries are everywhere, in your laptops, in your cell phones, and almost everywhere. Hello? Is there any problem, Kiran?
No, ma'am, it's all right. Actually, someone, okay, unmute their mic. You please go ahead.
Okay. Well, so that's what I was telling, that initially when lithium batteries were invented, lithium metal was used as an anode, and there was some safety issues. So John Goodenough come up with the metal oxide based cathodes, and then this Japanese gentleman has invented a graphite anode, and that is how this battery has become more safer and commercially viable, and that is deployed in almost all electronic gadgets today. Okay, so you must have noticed that I was saying that rechargeable battery when I mentioned a lead acid battery. So based on that, there are two types of batteries. One is called as rechargeable batteries and another is non-rechargeable batteries or primary batteries. Why this differentiation of classification is there? Because you must have seen that there are some batteries that we use in our remotes or children's toys. We can use them once, and once the energy that those batteries are storing is finished, then we have to throw them, right? We cannot charge them repeatedly. So that is because of the chemistry of those batteries. So based on that, the batteries can be classified as rechargeable and non-rechargeable. So in general, the electrochemical reaction occurring in these cells is not reversible. So that's what makes these batteries unrechargeable. So as I said that the batteries in remotes and toys are based on zinc, carbon or alkaline based chemistries, and we have to discard them once they are completely discharged. But in case of rechargeable batteries, they are also similar to primary batteries. Only difference is that the redox reaction that happens in that battery, it is reversible. Okay, we can keep on doing that redox reaction again and again by charging them by pushing in the electrons in that specific battery. Of course, these batteries also have certain life. We cannot keep on doing that indefinitely, but still they can go up to thousands, multi-thousand cycles of charging and discharging, and that's why they are called as rechargeable batteries. So apart from lead acid and lithium ion batteries, there are other types of rechargeable batteries are also that are available commercially. As you can see here in this table, that is nickel cadmium battery or nickel metal hydride battery, that's all. We can see that overall performance comparison as a cell or as a battery. So among all these secondary batteries, the nominal voltage of lithium ion batteries is maximum, and therefore energy density is also more in case of lithium ion battery, because energy density is directly proportional to the cell voltage. Okay, so power density, you can see here, power density and cyclability of nickel metal hydride batteries is comparable to lithium ion batteries, but nickel metal hydride batteries have severe self discharge issue. And then nickel cadmium batteries have comparatively less self discharge, but they suffer with an issue called as memory effect. If you want to know more about self discharge or memory effect, you can ask me at the end of the talk. I'll explain you. Okay, so that's why lithium ion batteries are more popular for most of the electronic devices, and that can be visible here in the revenue share contributed by different battery chemistries. So based on these chemistries, they are classified like this, and you can see that at 37% revenue share, lithium ion battery is the battery of choice for portable devices. Well, so this is about a different kind of batteries. I'll explain you the difference between lithium batteries itself now. All lithium batteries are not lithium ion batteries. Okay. What happened? Like initially when lithium battery was invented, it was not a secondary or it was not a rechargeable battery. It was a primary battery. And as I said, lithium metal was used here, and manganese dioxide was used as a cathode. So this battery was not safe because lithium metal used to deposit in the form of dendrites on cathode side, and that's why it could poke the separator and there would be a short circuit and battery can explode. So later there were some modifications and inventions, and lithium metal battery has been made into rechargeable batteries also. But as I said, it was not safer. You must have heard somewhere that the first lithium battery has blown an entire airplane at that time, a long time back, and that has stalled the commercial progress of lithium metal battery. And then years later, then John Goodenough has discovered that probably a lithium metal complex like lithium cobalt oxide would be more safer option, and the Japanese scientist has discovered graphite is a more it can efficiently intercalate lithium but as an anode, so that is how they have made this battery more safer, and they then Sony has commercialized that battery. Here liquid lithium salt electrolyte is used. Usually it is dissolved in an organic solvent, so it is quite long life battery, and it is comparatively safer. So this is the present what I am saying about lithium batteries. In the present commercial batteries, there is another lithium-ion battery which is called as LiPo battery. If you have seen drones or there are some solid state batteries you must have heard about. So these are LiPo batteries. They are same as lithium ion batteries. Only difference is that the liquid electrolyte from lithium ion battery is replaced by solid state polymer electrolyte here. So generally gel polymers or solid state polymers are used as electrolyte here, and they are very lightweight. They have some safety, they have addressed safety issues actually, but the interface between electrode and electrolyte is not as good as in case of liquid electrolytes here. So there are certain issues, but still these two types of batteries are commercialized. When it comes to lithium batteries, these are called as the future of lithium batteries. One is lithium sulfur batteries. Here, lithium metal oxide cathode is replaced with elemental sulfur, because elemental sulfur has very high specific capacity, which can increase the overall energy density of lithium batteries, and they can make it way more viable for electric mobility. But there are certain issues in using elemental sulfur because it is not conducting, and then it can undergo severe volume expansion during charging and discharging, and then there is intermediate polysulfide formations which can dissolve in the electrolyte, and that has made this battery it cannot go beyond certain cycles. So that's why a lot of research is going on this type of battery, and it is said that maybe the most recent future for lithium ion batteries would be lithium sulfur batteries. Even my group is also working on this type of batteries. And then the distant or the ultimate target for lithium batteries would be lithium air batteries. So here the idea is that to use the oxygen from the air as a cathode. So what happened here that when half cell reactions in here in case of oxygen, it reacts with lithium anode and it forms lithium peroxide. So as straight is like this lithium peroxide formation is reversible. It sounds really simple right here, but it is not as simple as it sounds, and there are certain issues with this kind of lithium air battery, because lithium can vigorously react with air. That is one of the issue also here, and so cell design is also one of the problem with this kind of batteries, and that's why people are working on these lithium air batteries as well, but it is not yet commercialized, even lithium air battery also. So this is all about lithium batteries. Now I'll talk about lithium ion batteries specifically. Before that, I would like to show you this video. You can see here. I hope that the video is running, right? So can you see the video?
Yes, ma'am.
Okay. So what happened here that during charging, that lithium ion can intercalate into graphite anode, and then the battery gets charged. And during discharging, the lithium ion migrate back through the separator or electrolyte, the cathode, and the electrons can flow through the external circuit powering our devices. So this is the basic of lithium ion battery. You can see here exactly what kind of reaction happens. So this is the cathode half cell reaction, and this is the anode half cell reaction. So during discharge, lithium ion migrate towards cathode, where they are incorporated into lithium cobalt oxide, which reduces cobalt from +4 to +3 oxidation state. Okay, so in case of lithium batteries, reduction and oxidation are quite relative terms. So we generally consider them based on discharge reaction. So here the discharge reaction is that lithium cobalt oxide reduces cobalt from +2 to +3 oxidation state. And on the other hand, lithium is oxidized from lithium to lithium plus, that is 0 to +1 oxidation state, while deintercalating from graphite. So this is reversed during charging, and lithium ions leave lithium cobalt oxide cathode and migrate back to anode, where they are reduced back to neutral lithium and reincorporated into the graphite network. So in almost all commercial lithium-ion batteries, graphite is used as anode and lithium complexes of metal oxide are used as cathodes. You can see here table, but you can see that there is a lot of development on cathode side. Several lithium metal oxide complexes are developed on cathode side based on different applications because their nominal voltage is different, and then there are some safety issues, some cost issues are also there. So based on all this, these different cathode chemistries are well developed, and these cathode chemistries are also commercialized as well. So you can find all these cathodes in commercial batteries for different applications. But in all lithium ion batteries, anode is always graphite. Okay. So now I will tell you, we will go more deeper and deeper into lithium batteries. So I'll tell you on what basis we can say that this material is cathode or this material is anode. So generally, this assumption is considered to decide anode and cathode. This is the energy diagram of electrolyte. You can see here. So the choice of electrode depends upon the electrochemical potential values of the anode and the cathode and their relative position with respect to HOMO and LUMO energy gap of the electrolyte. So for a stable cell, the electrochemical potential of anode should be lower in energy than the LUMO of the electrolyte. Otherwise, electrolyte will be reduced. And on the other hand, for the electrochemical potential of cathode should be higher in energy than the HOMO of the electrolyte to inhibit the oxidation of the electrolyte. Okay, so a high energy storage density can be obtained if this the electrochemical difference between anode and potential difference between anode and cathode is higher. But at the same time, we have to think about the stability of the electrolyte as well. So based on this, there are certain materials that are identified as anodes and cathodes. You can see here, this is capacity versus voltage diagram for cathodes and for anodes. So you can see almost all the cathodes have maximum specific capacity less than 400 milliampere hour per gram. But in anode side, there are materials which can have very high theoretical specific capacity, more than 4000 milliampere hour per gram also. But these materials are not commercialized despite of having such a high theoretical specific capacity. So why they are not commercialized, that's what I'm going to tell you now. But before that, I'll just tell you so these are different cathode chemistries as you can see here. So mostly the cathode materials are transition metal compounds, oxides or complex oxides, and these transition metal compounds have layered and then spinel and Olivian crystal structures. And transition metal cations, they typically display 4 and 6-fold coordination with oxygen anions or anionic clusters. Lithium ions are inserted via an electrochemical intercalation reaction here, and while lithium ion occupy the space between adjacent layers or unoccupied octahedral or tetrahedral sites, at that time equal number of electrons enter the available d orbital of the transition metal cations in the host crystal. Right. The ideal cathode materials should have good thermal stability, high voltage, and then high lithium mobility and capacity. Well, this is not my area of research, but I'm just giving you all the introduction of the components that are important to determine the performance of a battery. I work on anode materials, so this is my favorite part to explain to the students specifically. Anode plays a crucial role, as I showed you that they can have very high theoretical specific capacity. So the characteristics of anode can directly influence the battery's electrochemical performance. Physical and chemical properties of anodes active materials actually determine the battery behavior, and that's why it is very important to consider them and control them appropriately. So there are broadly these 3 types of anode materials that are known today. First is intercalation type of anode material, and then alloy type of anode material, and conversion. So the current commercial graphite is based on this intercalation type of anode. So here lithium ion intercalate into crystal lattice or layers of host material, mostly graphite, during charging, and de-intercalates during discharging. So as I said, that all the graphite-based batteries are working on this principle, intercalation principle. Here, the crystal structure of the host material remain intact even during the multiple charging and discharging processes, and the changes are very minor or very insignificant. So that's why these type of materials can undergo several charge and discharge cycles without fail. But comparatively, they store very less energy because when lithium ion intercalate in carbon or graphite type of anode, 6 carbon atoms can hold 1 lithium ion. So that gives us theoretical capacity of around 375 milliampere hour per gram. And practically it is much lower than that actually. So these are second type of materials. They actually undergo phase transformation during charging and form an alloy with lithium. Okay. And during discharging, they undergo de-alloying. So this alloying and de-alloying is reversible here. It occurs reversibly during charging and discharging. So they have theoretical specific capacity which is 2 to 10 times higher than carbon anodes. Alloy anodes have their own problems also. That's why they are not yet commercialized. They have like mostly tin and aluminium, magnesium and silicon are used as alloying anodes. So most of them are semiconductors, so their electronic conductivity is not very good, and they go through very large volume changes during lithium ion intercalation and de-intercalation process. So that brings about several issues like high reversible capacity loss and rapid loss of capacity in use. I'll explain this to you in the I'll show you one of the examples from our own research to explain you how we can, what are the issues with this type of anode and how we are trying to control them. Okay. So third type of anodes are convergent type of anodes, and they actually undergo reversible redox reaction during charging and discharging. So most of the transition metal oxides are convergent type of anodes. Even sulfides and phosphides are also can undergo this principle in batteries. What happened here, when metal oxide reacts with lithium, it forms Li2O reversibly. So there is a multiple electron transfer, and that's why the energy stored is also very high here. But again, the volume expansion and voltage hysteresis issue has impeded the commercial viability of conversion anodes. So a lot of people are working on this also. For this also, I'll show you one example from our research group that what we are trying to do to control while getting more energy from this type of anodes. Okay. So before showing you the examples from our research, I will just tell you some more concepts for lithium-ion batteries itself. So electrolytes is also one of the important part of lithium-ion batteries. They are often overlooked when it comes to battery performance because they do not affect the stoichiometric theoretical electron storage capacity of the battery. Okay, only anode and cathode materials can affect the theoretical specific capacity, but electrolyte and separators can affect the charge transport within the battery. Okay, so this charge transfer ultimately affect the deliverable energy content under specific application. So it is very important to select a suitable electrolyte for a pair of electrodes in lithium-ion batteries. These are the mostly liquid electrolytes which I was telling you that are being used in lithium-ion batteries, which are commercially available now. So they are basically carbonate-based solvents are there, and lithium salts like lithium hexafluorophosphate or sometime even lithium perchlorate that are dissolved into these organic carbonates, alkyl carbonates or propylene carbonates, ethylene carbonates, and used as an electrolyte. So these are liquid electrolytes. They are very good. They are having very good ionic conductivity and charge mobility or ionic mobility is also very good in these type of electrolytes. But they have some safety issues because they are highly volatile and flammable. So reducing the flammability of the battery electrolyte is one of the strategy to increase the safety of the batteries, especially when most of us are not aware about how to use our electronic gadgets and we abuse them. We keep our cell phone charging for overnight. So it keeps on charging even when it is fully charged. So the advanced cell phones have those electronic circuits which can stop your electron flow through your battery after certain when your battery is 80% charged. But some cheap mobile phones or cheap batteries that are available in market may not have this kind of safety circuits or safety provisions in your cell phone, and that's why cell phone can explode if you do not follow the instructions of charging and discharging, right? So towards this end, ionic liquids are also being investigated as a possible alternative to conventional electrolytes. Ionic liquids are known since long time, but their study as battery electrolytes is quite recent. I don't know much about ionic liquids, but I think one of the issue about them is higher viscosity than the conventional solvents. I told you about LiPo batteries also, right? Lithium polymer batteries. So there solid polymer electrolytes are used. So these solid materials are typically non-flammable and they cannot leak, obviously. So that's why they are very safe to use in lithium ion batteries, right? But as I said that these can have issues like a proper electrolyte interface, and here most of these lithium polymer batteries have lithium salt dissolved in polymers like PO. PO is very commonly used, polyethylene oxide. In some cases polypropylene oxide and polyethylene glycols are also used. There is a lot of research going on this type of solid state electrolytes like inorganic electrolytes, where inorganic nanoparticles are mixed with superionic conductors. I don't know if you have heard about superionic conductors like lithium superionic conductors and all. So they are into like investigatory stage. They are not yet commercialized. At least polymer electrolytes are quite progressed in commercial devices also, but composite electrolytes of inorganic materials are not yet commercialized. As I said that there are two challenges that needs to be overcome before these solid electrolytes can be widely deployed. First is their ionic conductivity is much low than liquid electrolytes, so that prevents fast charging and discharging. And the second is forming a stable conductive interface between solid electrolyte and electrode is difficult. Okay, so that is very important for charge mobility or charge collection, the interface formation. So that is highly what you can say efficient in case of liquid electrolytes. Well, this is about electrolytes. Then these separators is also one of the component that people are doing research on. A lot of material scientists and polymer scientists are also working on this separators. So the function of separator is that it should allow the electrolyte ions or the lithium ions to pass through it, but it should act as an electrical insulator. So it should prevent the contact between an anode and cathode. So a characteristic separator should have good chemical stability, mechanical strength, and then thermal stability. It should have high wettability for electrolyte. It should have a proper porosity around this 20 nanometer to 100 nanometer, and then permeability. Thickness also matters. Also, there are certain tri-layer electrolytes which are function in a way that if a battery heats up, this separator becomes solid. It shrinks and it closes its pores and saves the anode and cathode. It doesn't allow the anode and cathode to come in contact with each other. So a lot of these kind of things are happening here. Most of the time, like whatever commercial batteries, even in my lab also, we use separators from Celgard to test the materials, electrode materials that we develop in our lab. So Evonik and Celgard are the companies who are dominant in separator industry. Now a lot of polymer scientists are doing research on making electrospun nanofiber mats for using as a separators. They have a lot of advantages like higher porosity and permeability and better wettability, and also nanofiber layer with porosity above 90% can reduce the resistance to ionic current and allows higher transfer of lithium ion. But it is all in the exploratory stage, as I said. One of my colleague in NCL also working on this aspect of lithium ion batteries. Okay. Well, I have told you about different kind of materials or components in the batteries and different chemistries that are related to those materials in the batteries. So all these battery active materials are evaluated through a lot of material characterization techniques for fundamental understanding at research level in our labs, like we do XRD, XPS, Raman spectroscopy, BET porosity measurements, and several kind of these characterizations to understand the structure to activity relationship between these materials. Okay, and they are also being done for comparative analysis and then for quality control in manufacturing stage also. So all these give us an idea about the battery materials, structural and functional properties, but electrochemical properties of the active materials are also need to be investigated and validated specifically for batteries to claim their performance. Okay, that this battery can or this material can have this much of capacity or this much of energy density. For that, we need to do some sort of electrochemical test. So this analysis is very time and material intensive, and generally it requires electrode fabrication, then cell assembly, and then cell cycling. And in addition, evaluating active materials electrochemically in battery cells can be complicated by electrode microstructure as well, and the contribution of other components within the cell, because we have to fabricate the cell to test them electrochemically. So there are certain components which are not active, but they can add up the complications in the test. So there are a lot of electrochemical tests that we do in our lab to understand the electrochemical behavior of the materials that we are developing. I will show you just few examples of these tests which are most important to define or to determine the performance of the material or the performance of the battery based on those materials. Okay, so one of this is charge discharge measurement. It gives us idea about how much charge capacity a material or cell can store. It also gives information about cycle life and rate capability. So this is generally done by galvanostatic chronopotentiometry. Okay, so this is one of the electrochemical technique. So in galvanostatic potentiometry, the change is plotted in potential versus time at constant current. Okay, so constant DC current is applied to the electrode while it is immersed in the electrolyte. So then capacity can be calculated. You can see here capacity is plotted. So capacity can be calculated by integrating the current in the time. So we generally calculate it from discharge time and current obtained from these charge discharge measurements. Okay, so another important electrochemical test for battery materials is cyclic voltammetry. So this is commonly employed to investigate the reduction and oxidation processes of molecular species. So this is you can see CV shown here. You can see here it is a type of potential dynamic electrochemical technique. Okay, so what happened here in a typical cyclic voltammetry experiment, the working electrode potential is ramped linearly versus time. Okay, and after set potential is reached in a CV experiment, then the working potential is ramped in the opposite direction to return to the initial position. So these cycles of ramp of potential can be repeated as many as time needed, and then current at the working electrode is plotted versus applied voltage. Okay, so it gives us then cyclic voltammogram trace as shown in this figure. But the CV shown here is a simplest form of CV, and you can see that there are clear-cut reduction oxidation peaks here. But in case of battery materials, the CV is not so simple, and we can often get a very complex voltammograms with multiple peaks for multiple electron transfer. So analyzing and interpreting them is not so straightforward. Okay. Then this is the test that defines the battery's life and the how fast we can charge and discharge the battery. So this is cycle life test, and this is rate capability studies. They are very important because, and they can be estimated from this charge discharge measurements itself. Only we can do this charging and discharging for the multiple times for several thousand cycles. And rate capability is done at different C's. Okay, you can see here, but there are different C rates are shown here, and then specific capacities measured at those different C rates. So what is this C rate? So C rate is usually used to signify the charge or discharge rate equal to the capacity of a battery divided by 1 hour. So thus, one C rate, suppose we take a 1600 milliamp hour battery. So one C rate would be 1.6 ampere. Then C by 5 for the same battery would be 320 milliampere. C by 10 would be 160 milliampere. Okay. So C is depend on the capacity of a battery. The C rate for the batteries of different capacities will be different. So that is of the that we test in our lab also. Even if for material also we do C rate testing, because we know the theoretical capacity of material. So based on that we can calculate the C rate, the current that we are applying to get this curve. Okay. Well, this is all about the battery chemistry and the components and the electrochemical tests that we are doing. So different cell chemistries, I have told you about different battery chemistries, then the different chemistries in lithium batteries itself, and then the chemistry in lithium ion batteries. Okay, the different anode chemistries and different cathode chemistries as well. So all these different cell chemistries define the essence of a battery, and they lay the foundation for its suitability for specific applications. Okay, but despite of this important electrochemical background, sometimes it is the packaging that influences the important parameters of a battery, most specifically the cost of the battery. So these forms can also define how costly your battery would be. They also define the lifetime. Sometimes they affect the cyclability also, the ruggedness and the safety of the battery also. As I said, and they also influence the cost of the battery. So in case of lithium ion batteries, cell packaging is done in these kind of different forms. So this is a prismatic cell, this is cylindrical cell, this is called as pouch cell, and this is a coin cell. I'm sure you must have seen these type of cells somewhere, at least because they are part of our routine life, everyday life, right? So batteries in your mobile phones or digital cameras or video cameras or tablet computers, they have such kind of box like appearance, right? So those are prismatic batteries. Your cell phone battery is also prismatic batteries. So there is no standard size or aspect ratio for prismatic batteries. They utilize space quite efficiently, and there is flexibility in designing also. But they are very expensive to manufacture, and they are less efficient in thermal management. So then cylindrical batteries, these are early form of mass produced battery. You have seen even voltaic pile was also kind of similar kind of cylindrical battery, right? So this is the earliest form of mass produced battery, and this is very popular today also. So biggest advantage of this cylindrical battery is the mechanical stability of the cylinder, because it can naturally withstand the internal pressure without deformation. And then pouch cell has been invented quite recently. So pouch cell has literally surprised the battery world with this radical new design. So instead of using this metallic cylinder or glass to metal electric feed through, here also glass to metal electric feed through is there, they have used these conductive foil tabs that were welded to the electrodes and brought to outside in a fully sealed way. Okay, so this pouch cell makes most efficient use of space and achieves 90 to 95% packaging efficiency. So this packaging efficiency is highest among the battery forms, and that's why many applications these pouch cells are being used in, specifically where you need lightweight batteries. Because eliminating these metal enclosures has reduced the weight of this battery drastically. Even in pouch cells also there is no standard size. In case of cylindrical cell, there are standard sizes, but for pouch cell and prismatic cell, there are no standard sizes, and every manufacturer make their own designs as per the application that they want to use it in. These button cells are now they are not being used as much. I think you must have remembered that in old times in our clocks or maybe wristwatch, we used to have these type of button cells, right? But now today, most of these button cells are non-rechargeable, and they are generally used in medical implants or hearing aids and car keys. This even in our lab also, we use button cells to test the materials that are synthesized by us, because fabricating this type of batteries is quite, you need a lot of intensive facilities for that, but this is relatively easier. I will show you how we make these coin cells in our lab. Okay, so these are the indigenous cells, cylindrical and pouch cells, that are developed by CSIR. There was a large 5-year program called TAPSON. I was also part of this program. CSIR SICRI was the leading lab for this development. In the end, I'll tell you more detail about this. I'm just showing here that this is the battery that has been fabricated based on the materials that are developed by CSIR, and it is fabricated in a CSIR facility itself. Okay. Well, all this about battery components and then electrochemical tests and battery forms. The single cell configuration is the simplest battery pack. We see in our cell phone there is a single battery, right? So it does not require any matching or any BMS that can handle the different batteries, or typically like mobile phones or tablets, they have 3.6 volt lithium ion cell, which is a single cell. So if we strictly speak, battery is a term that is used for multiple cells that are connected together to provide a source of potential difference in this circuit. Even historically also, the term battery is specifically referring to the device composed of multiple cells. Single cell is generally not called as a battery, it is called as a cell only. So just like any other electrical component, individual cells can be connected either in a series or in a parallel here. So in series, the voltage sums up to create a battery with higher voltage, but current remains same here. Okay, so current will be same as of a single cell, and the voltage will be increased on adding multiple cells or connecting multiple cells. In parallel connections, the batteries have the same voltage, but the current is multiplied here. So we can create a battery of higher current by connecting multiple cells in a parallel. So what generally most of the applications require certain voltage and certain current, which is not probably may not be enough that we are getting from a single cell. So such type of parallel and series configuration, this is the simplest form I am showing you here, but many complicated parallel and series configurations are generally being made, designed to achieve desired voltage and current for the typical application. Okay. Well, this is all about the basics of the lithium batteries, or the chemistries and their components and their connections, testing and all. Now I will show you how they are being used in electric mobility or electric vehicles. Okay, if you see this graph here, this shows us the energy and power requirements of vehicles, right from starting, lighting, ignition to a complete EV. So you can see here that for a complete electric vehicle, we need at least 20 kilowatt hour of energy. So these figures are based on 100 miles of run in a single charge. So to run a passenger car for 100 miles in a single charge, we need at least 20 kilowatt hour of energy. So that is quite huge, right? So these small single cells do not have this much energy. So how many cells would require to make this kind of big battery? So I'll show you an example of the today's hottest passenger car, that is Tesla's Model S. Somebody was telling me that Tesla has done a battery invention. So yeah, Tesla is doing a lot of battery inventions, because the Tesla's founder think that fuel cells are bullshit. He says that fuel cells are good for rockets, not for EVs. So he is investing a lot in batteries. So I'm showing you here the battery pack, Tesla's Model S battery pack. You can see that this battery has occupied the entire floor of this sedan. This is 100 kilowatt hour battery pack. So it can go 550 kilometer in one charge. Okay. So this is a huge battery pack. You know how it is made? It is made with such small single cells. We call them 18650 single cells. So thousands of such cells are connected together to make modules module, and then 16 such modules are connected together to make this huge battery pack to get this kind of 100 kilowatt hour of energy from this battery pack. So this is very big. It is, as I said, that it is occupying entire floor of this sedan, and it also contributes to the 25% weight of this car. So that is why there are a lot of efforts are going on to reduce the weight of this battery pack. Of course, we need to add several DAY components here in terms of thermal management system, safety coverings and safety protocols we have to use while making battery packs. That also increases the weight of the battery pack, and there are automotive engineers who are working on those DAY components, making them from lightweight materials to reduce the overall weight of the battery pack. But as a material scientist, we can also reduce the weight of the battery pack. As I said, the engineers are also working on different components. So one another car manufacturer like Nissan Leaf is also another hottest passenger car, passenger EV electric car. So they have used this 40 kilowatt hour of battery pack. So they have reduced the weight as well as size of their battery pack slightly, because they just changed the form of the battery. So instead of cylindrical cells, they have used these pouch cells. So pouch cells, as I said, they can give you highest packaging efficiency, and they are very light in weight, lighter than the cylindrical cells. So by changing the form of the battery, they could reduce the size and the weight of the battery pack. But still it is quite huge. Though there is a slight decrease in the weight and size, it is not still not ideal for an EV. The efficiency of the battery defines the efficiency of powertrain, but the efficiency of vehicle is always defined by the weight of the vehicle. That's why it is very important to reduce the weight of this battery pack. So Nissan has done this, but as I said, as a materials scientist or chemist, if we can pack more energy in these single cells, then the cells required would be less in a number, right? So that can reduce the size as well as weight of the battery. So I'll show you the flow, how from powdered materials the electrodes are fabricated, and then from those electrodes cells are fabricated. Then these multiple cells are used to make a module, and then different modules are used to this battery management system, which is ultimately goes into the battery pack of the vehicle. Okay, so Tesla uses this 250 watt hour per kg batteries. If for 100 kilowatt hour, the battery weight itself would be 400 kilogram. So it is mandated that maybe by 2030, so the weight of the battery pack should be reduced to 235 watt hour per kilogram. That is mandated, and a lot of research is going on in that. So as I said, whether it is a pouch cell or whether it is a cylindrical cell, the important components are same: anode, cathode, separator, and electrolyte. So more or less the chemistry is same here. If we play with the chemistry, then we can play with the energy density also, the energy that is being stored in the single cells. So there is the scope for material scientists to increase the overall energy density of the battery. Even Nissan Leaf has done that. So they have just changed their cathode chemistry. So their first generation EV battery had this lithium manganese oxide, and then they have changed into nickel manganese cobalt oxide. So by changing this battery chemistry, they have again reduced the size of their battery packs. But this change is also not that significant, as I said. And this change can be drastically significant if we can achieve a breakthrough on anode side. They have done this on cathode side. That is where my research group also works on. We work on alloying type of materials, conversion type of materials. We are also working on intercalation type of materials as well, because they are very rugged. They do not deform over multiple cycles. So we are trying to play with their morphology and their surface chemistry to increase the inherent specific capacity of these materials. My group also works on flexible supercapacitor devices, and then we are working on futuristic batteries like lithium, sulfur, or sodium ion batteries as well. Okay. So this is what we do, but I'll show you the examples of these three types of materials. Just one example from my research group. Before that, I will tell you what are the challenges for such kind of high energy density materials. So we'll take an example of silicon. Silicon is an alloying material. Okay, so theoretically it has very high specific capacity of nearly 4,000 milliampere hour per gram and quite low delithiation potential. So it makes ideal anode material. But the issue is that silicon has severe volume change. So that's why the cycle life is very poor. So these are prominent material related issues for silicon. What happened? When silicon alloys with lithium, so I told you that in case of intercalation, 6 carbon atom can hold 1 lithium. But here, 4 lithium atom can intercalate with 1 silicon atom. 4 lithium ions can intercalate with one silicon atom. Okay, that's why this silicon undergoes large volume expansion, nearly 400% than its original size during alloying reaction. Okay, so what happened then when de-alloying reaction happens? Then when lithium ion de-alloy from this silicon particle, it cannot sustain that you can say strain due to this volume expansion and contraction, and the electrode cracks like this. So after a few cycles, the electrode completely disintegrates and the battery stops working. So it has been envisioned that probably nanoparticles can contain this issue, strain-related issue, more efficiently. But it has been observed that even nanoparticles also undergo volume expansion and contraction. Though they do not crack, they tend to disintegrate from the current collector because of this issue. And that's why after a few cycles, again, the battery stops working. And the third most prominent issue in case of silicon kind of material is dynamic ACI layer formation. So what happened here? ACI is solid electrolyte interface layer. I was telling you that a proper good interface between electrolyte and electrode surface is very important in case of batteries for efficient charge collections and for overall battery performance. So here, what happens that when first time electrolyte comes in contact with electrode surface, some irreversible reaction happen on the electrode surface and a gel-like thin polymeric layer forms. We call it as a solid electrolyte interface layer. So as long as this layer is very thin of nanometer level, nanometer thickness, it is good because it acts as a lithium tunneling layer. So it allows lithium ion to pass through it, but it protects the electrode surface from further decomposition, you say, like it doesn't come in contact with electrolyte because of ACI layer. So electrode is protected in that case. But in case of silicon, what happened that every time when during charging, discharging, when such electrode particle get cracked, the fresh electrode surface get exposed to electrolyte. And electrolyte again reacts with electrode surface and form the ACI. So during every cycle, ACI layer forms here. That is why we call it dynamic ACI. So after a few cycles, it becomes so thick that it just doesn't allow lithium ions to pass through it. And again, battery fails. Okay, so these are the issues with silicon. So I'll show you just one example. My group is doing a lot of work on silicon anode, but I'll show you one example to what we have done to contain this issue. Okay. So generally, we use copper as a current collector towards anode side particularly. So planar copper foil is used. So these planar current collectors do not offer any protection or any buffering for this kind of high energy density materials. So here we have tried to make a porous three-dimensional current collector. So we have done this chemical vapor deposition process, and perfluorohexane was used as a precursor. So at high temperature like 900 degrees Celsius, this perfluorohexane decomposes into carbon and fluorine. So fluorine is known as an etchant of metals. So here we have used stainless steel as a substrate. Instead of copper, we use stainless steel. Even stainless steel can also be used as a current collector on anode side. And then this carbon, it gets deposited in the form of graphene at this temperature inside this tube furnace that we have used for CVD process. So you can see that this is the SCM image of this porous current collector. So simultaneously, pores are created in the stainless steel, and graphene is deposited on this porous current collector. And then we have loaded small silicon nanoparticles inside the pores, you can see here. And then we have done second deposition of this graphene layer with same process. So the ultimate final electrode has silicon as active material with bottom graphene contact as well as top graphene cover. So you can see here that single silicon particle is engulfed in the sheet of graphene like a blanket. So these are TM images. We have done all characterization, material characterization, but I'm showing you just Raman spectra here. You can see this black graph. You can see how pure the graphene deposited here. There is very, very small defect peak is here. That is probably because of this curvature of these pores, which can deflect the graphene crystal lattice, and that's why. Otherwise, it's highly pure, and you can see a very large and sharp 2D peak that exemplifies that the graphene deposited here is either single or just few layer graphene. And then after silicon deposition and then second graphene, then the defect peak has slightly increased, you can see here. So idea here is that this silicon nanoparticle has bottom graphene contact also, because silicon is semiconductor, as I told you in the starting. So this bottom graphene acts as an efficient charge collecting layer, and then this top graphene blanket, it protects silicon particle from breaking down during volume expansion. This was the idea. So we have made samples with and without this top graphene layer also, and then studied in a coin cell. So we made coin cells of these electrodes, and we have done this electrochemical testing, which I have showed you in the earlier slides. So you can see that this is without second graphene layer. You can see that there is a large, this is the first cycle discharge, and this is it with second graphene layer. The graph also becomes quite stable in its profile, and then the capacity loss is also decreased here. We have done rate capability as well as cycle life study. So you can see here that for 1000 cycles it is quite stable, which is very, very good for silicon, because silicon cannot be cycled beyond 5 to 10 cycles. You can see this is actual instrument data. This is without graphene layer. Within few cycles, the cell stopped working, and even these initial few cycles are also not uniform. But when there is second graphene coating, very uniform charging and discharging we could get. Well, this has been published long back. We are now working on more scalable approaches, which we can like this help us to understand silicon as an anode material. But CVD is not, it's not scalable process. So we are working on more chemical processes which we can scale up, and we can synthesize the materials in kilogram, because as a CSIR scientist we are mandated to do the research that is electrochemical, that is industrially viable. It should be appealing to the industry, not just science or fancy science. So we are working on that aspect. I'm not going to show you. I'll just show you another example of conversion anode, which I was telling you about during earlier slide. So here I told you that metal oxides undergo redox reactions reversibly, and that's why they are called as conversion anodes, right? So here we have taken iron oxide, and then we have taken one metal hydroxide also to make a composite. Why we chose metal hydroxide? Because in case of metal oxide, I said that it forms Li2O reversibly. In case of metal hydroxide, it first forms LiOH and then it forms Li2O. So there is additional electron transfer here that can give you more capacity. Okay, not only that, because oxide and hydroxide, they do not undergo reduction and oxidation simultaneously. They do it sequentially. So when one component is going through reduction oxidation, the other one holds it. Its volume expansion or its voltage stresses kind of issues can be, they can be significantly buffered by this component. And when this is going through reduction and oxidation, this component can hold the issues of this hydroxide. And then we have used carbon nano onions. These are small carbon nanoparticles. as an you can say percolating conducting network, because again oxide and hydroxides are not highly conducting. So this has been used for efficient charge collection, and that is how we made this composite, ternary composite. Again, in coin cell we have tested them for charge discharge, cycling stability and rate capability, and all like CV and all. So you can see here that the cycling stability we have done for 1000 cycles for this ternary composite, and it is quite stable. And even capacity is also very high, around 600 milliampere hour per gram, which is much more than intercalation anodes. Okay, so one of my student has done her entire thesis work on this conversion type of anodes. She is now working in IIT Delhi. So she has made such kind of different compositions of convergent type of anodes. Then there are some hybrid materials also, which can store energy based on conversion cum alloying principle. Okay, so here mostly I told you that not only oxides but phosphides and sulfides can also used as a conversion material. So phosphide is a very good conversion material, but when it is used in combination with some alloying material, its performance is always much better. So here we have used this tin phosphide composition, because tin is an alloying material and phosphide is a conversion material. So here this tin phosphide phase has been synthesized by one of my students, and nanoparticles are synthesized, and she has encapsulated them in a carbon matrix. So she has made electrospun carbon nanofibers by actually she has electrospun the fibers of polymer with this tin phosphide nanoparticles, and then she has pyrolyzed them to make carbon fibers that are incorporated with this SNP nanoparticles. So here phosphide, so there is a two type of energy storage reaction here that happens. Phosphide undergoes reduction oxidation and tin undergoes alloying and de-alloying. So another student of mine is working entirely for her thesis on this type of hybrid materials only. And she has made different kind of compositions of such kind of hybrid anode materials. Well, yeah, so I have just showed you some representative examples of such high energy density materials, but still to deploy them in commercial batteries will take much more optimization, and even the industry works on principle of benefit only. So we have to show them how they will be benefited by using those materials. So cycle life is still an issue for those kind of materials. So somebody said as Tesla has made invention, so I must mention that Tesla has announced that they have made a silicon based battery in collaboration with Panasonic. They have not disclosed exactly what kind of battery they have made from silicon, because in case of silicon, if you add a silicon nanoparticle, 10% silicon nanoparticle in carbon, it will marginally increase the specific capacity of your battery, but it will not exploit the entire benefits of silicon kind of anode. I think they must have done something like that 10%, or because there are a lot of spin-offs. There is one spin-off from US. It is called as Amprius. The Professor Waikwei's group who is extensively working on silicon anode. They are also mixing just 10% silicon with carbon, and they are claiming that they are made silicon battery. So it is quite interesting to know what kind of battery Tesla has made, but they have not made the invention public yet. Okay, so I was telling you that though how promising those materials are, it will take some time for them to see a commercial light. Okay. But carbon nanostructure, they are very well established and known as a good materials, good anode materials for batteries. Only issue is their theoretical specific capacity, which is low. So if we change their morphology and if we change their surface chemistry, we can store more energy on same carbon materials while what you can say extracting the benefits of having very good cycle life. So we have made these different kind of carbon materials. We have also doped them with heteroatoms like boron and sulfur and nitrogen. That has helped to increase their specific capacity, inherent specific capacity. And then we have scaled up this synthesis of porous carbon spheres. These are doped with nitrogen and sulfur. So with the help of, in collaboration with my colleagues from chemical engineering who are are having expertise in process intensification or scaling up the synthesis, we have scaled up this material and we are in talk with some industries for commercial, what you can say, the technology transfer for these carbon spheres. They are showing very good capacity as well as cycling stability in batteries. So this is all about the some research that is done in my research group so far. I will tell you now, like, see, I told you that when we synthesize this material, we test them in coin cells because we cannot test them unless we make a cell. So generally we make coin cells. So these are coin cell components. You can see here, this is the bottom part, and then this is the stainless. This is bottom part. This is the cap, and this is spacer, and this is the ring. So we generally assemble it in this way by keeping electrode materials and separator in between them. And after assembling all this, we have to crimp them inside a glow box. So I'll show you how we make electrode materials. So we generally synthesize powder electrode materials, right? And then we make a slurry by using some solvent. Usually, generally, NMP is used as a solvent here. And then we make slurry out of this. And then this slurry we coat on current collector. So you can see here that we have made a film on copper current collector. So all these processes are very important to extract the good battery performance. Even if you synthesize a very good material that has potential to give you very high capacity, if you do not make this electrode fabrication and battery fabrication properly, it will not show you that kind of good performance. Okay, so I have shown here 3 films that are deposited on current collector. This is not good because you can see there are several cracks on this film, so they can act as a hotspots, and then the battery performance will not be optimum. Here you can see that this film is thin at some places and it is thick at some places. This is also not good. So this is a good coating of electrode material. It should be uniform. There should not be any cracks on the film while coating the electrode materials. Okay. Then using such kind of cutters, different sizes, we can cut the electrode separators and anode and cathode side of electrodes. We can cut these circular discs from this coated electrode, and then using this crimping machine, we crimp them. Okay, we have to do up to this process we can do outside glow box, but to crimp the cell we have to do everything inside the controlled environment, inside argon filled glow box. So crimping is also very important. This is uncrimped cell, this is badly crimped cell, and this is good crimped cell. If you do not crimp cell properly, it will not give you again a good performance. So applying proper pressure and assembling properly the components is also very important. Okay, so these are some of the facilities that are available in my lab for battery work, like for synthesis of materials, then making electrodes, coating electrodes. This is roll press to make more uniform films. We can do everything in our lab, and then we do the cell assembly inside this glow box, and then we test them with electrochemical workstations also. Like electrochemical workstation, we can do all advanced electrochemical testing, including impedance and CV and all. And then we have these multi-channel battery cyclers as well, where we can do continuous charging and discharging for several thousand cycles. It depends on materials theoretical specific capacity. If there are high energy density materials, then it can take maybe a couple of months or sometime even 6 months, 1 year to charge and discharge the batteries for 1,000 cycles or 2,000 cycles. That's why we have many such multiple battery cyclers, so we can simultaneously charge and discharge 40 batteries at a time, because otherwise it would take too much time for this kind of research. Now recently we are establishing the pouch cell fabrication facility also. So we just need one more instrument that we have to keep inside glow box. We are in a process to procure that, but very soon we'll be able to make pouch cells as well. And then we have BET surface area analyzer also, because it is very important to understand the active surface area of the electrode material, their porosity, their pore profile and all, to correlate their activity as a battery material. Okay. So this is a team of my students who have done all this exciting work that I have shown you. Some of them have already graduated. This is my current group. So all these students have done this exciting work. I didn't show you the work that we have done on supercapacitors because talk was only on batteries. Well, that is all that has been done in my lab. Then at CSIR wide also there was a large program, I told you, for development of indigenous batteries, and Central Electrochemical Research Institute in Karaikudi was a nodal lab, and these were the participant labs who worked to develop this indigenous battery. So this battery has this cathode that has been developed by SICRI. Then multi-wall carbon nanotube based anode that was developed by CSIR NPL, and CSIR CGCRI has developed ceramic separator. NCL's contributions was towards this futuristic anode, silicon based anodes. That's where my group was contributing. It has not been used in the final commercial battery because, as I said, this was kind of futuristic work. So these batteries are fabricated in that program, and during in that program itself, CSIR has established this pilot plant level facility in the Chennai campus, or CSIR's Chennai campus. It is called as Abdul Kalam Center of Excellence of Energy. So here you can fabricate large scale batteries, but you need materials in kilograms to fabricate. This is a kind of manufacturing plant. This is the first kind of facility in India. Now several institutes are being funded to develop pilot plants for lithium-ion batteries, and even companies like Tata Chemicals, even Mahindra & Mahindra, and they are also coming up with their own battery fabrication facilities. Well, so this is the CSIR cell that has been, this technology has been transferred also, the RASI group, and there are several groups to whom this has been, this know-how has been transferred. So this is the CSIR cell, and it was compared to the commercial cell. You can see that the weight has been quite reduced while maintaining the specific capacity. So that's what I told you, that this is the kind of first lithium-ion pilot plant. That's all about CSIR, NCL's and CSIR's efforts for development of indigenous batteries. So this is a kind of roadmap for specifically for the requirements of electric mobility. So the generation 2 lithium batteries I told you about, they are based on lithium cobalt oxides, which are all commercialized. They are quite mature technology. And then as I said, that silicon anodes are being touted as a futuristic batteries that will be called as a generation 3 battery, specifically for electric mobility. For generation 4, I was telling you that lithium sulfur batteries or solid state batteries are being touted as generation 4 batteries, are being projected as generation 4 batteries, and the ultimate target is to make lithium air or lithium oxygen batteries, because their energy density is quite equivalent to gasoline. But the problem is that, as I told you, like the cell design and this reaction is also not, it's not efficient, because peroxide get deposited on anode side, and then so there are quite issues, and there are people who are working, but it is a tough from the materials point of view or from chemistry point of view also. But if we could achieve this, then this is the ultimate, because it will make the batteries more feasible, more portable, as well as they can store very high energy. So this is the roadmap. No matter what progress lithium batteries do and how much viable they become for e-mobility, for India, specifically for our country, lithium batteries still have a problem because we don't have lithium resources in our country. You can see here, this is the at least known lithium sources till date. There are a lot of work is probably people from Geological Survey and all, they are trying to find out new lithium resources. But as of now, among known lithium resources, India does not have any lithium source within our country. And you can see China has a large lithium resources. So most of the components, battery components, everything comes from China. You know how strained our relations with China as of now. So India don't want to be in vulnerable position again for when it comes to lithium batteries. So while promoting electric mobility, we have to think about this aspect about, because we are dependent on import even for petrol and diesel also, and now for batteries also we will be dependent on import only. That too from a country with whom we our diplomatic relations are probably worst at recent time. So what are the options for us when our entire world is moving towards electric mobility? The options are that we have to aggressively look for alternate chemistries like sodium ion chemistry, because sodium is abundantly available. We can see that all sodium salts that we can get from ocean can be converted into sodium metal. India is third largest exporter of sodium salts. So if we develop sodium chemistry and make it more viable like lithium chemistry, then that would be the best for India. Only thing is that sodium ion is little bigger than lithium ion. So sodium batteries are more heavier than lithium batteries. So I mean, people are saying that they are not really good for electric mobility, but there is a company called Faradian in UK. They are aggressively promoting sodium battery for electric mobility also. Okay, then a lot of work is going on solid state batteries as well. There is a lot of potential for solid state batteries to reduce the weight of the batteries. Some multivalent chemistries are also very promising, like magnesium or calcium ion, because you can see that they have multivalent electron. These are multivalent ions, so they can transfer more electrons per reaction, and that's why the energy stored can be very, very high. But there are a lot of issues with magnesium or calcium or aluminum based chemistries. We have recently started working on these alternate ion chemistries also. Then there are redox flow batteries as well, which are more or less similar like fuel cells. They are kind of hybrid between battery and fuel cells. I think somebody in SECRI is working on this technology also, but I am not much aware about redox flow batteries. I don't know much about them. Well, another immediate solution for us is recycling of battery materials. It is very important to create this recycling value chain for the lithium batteries that we are. See, recently our Transport Minister, Mr. Gadkari, has announced that they have taken 2 lithium mines in some South American country on lease. So a lot of lithium is going to be mined for India, and we may not be entirely dependent on China, but still we have to create this kind of value chain of recycling of the existing batteries. You know, these batteries, when we throw, they are not entirely, you can say, useless. Especially in electric mobility, we cannot use the battery once it goes down to its initial charge, state of charge, it becomes 80%. We have to throw them. We cannot use the battery that has become like from 100 to 80% state of charge is reduced. We cannot use it in EV. So these batteries can be used for secondary stationary applications, but after that also, when the state of charge becomes as low as 40% or 30%, we generally discard them. But still, the battery materials that are used in those lithium batteries are useful. We can extract them, recycle them, and we can extract value-added products from them. So simultaneously, India is establishing this recycling industry also. Our government is aggressively funding and subsidizing this recycling industry. I myself have a collaborative project, DST project, with one recycling company in Bangalore, and they have now established a very big plant on the border of Karnataka and Andhra for recycling of lithium batteries itself. So we are trying to see that if those extracted anode materials, how much we can get, again, if we reuse them, we refine and reuse them in secondary batteries, how much charge we can extract. So this kind of work is also important for us for immediate solution of this geopolitical issue of lithium resources. Well, that's all about batteries and all. I hope because I think listening one person's monologue for 1.5 hours is quite torturous. But I hope I have entertained and I have given you some kind of insights into batteries, which probably you might have liked. I don't know. Well, so I'll end my talk with another story. I have told you one story in the starting, story Galvani. So I will end with another story, story of quadrants of scientific research. These quadrants of scientific research are these theories proposed by one of the professor of political science in US. So he suggests this theory. He says that this is a Bohr quadrant. So this quadrant is, this type of scientists are they are more interested into pure basic research. They go deep and deep into every phenomena that they observe around, and they it is more of a quest of knowledge. So the way Bohr has discovered and told us about the atoms and all, so it has enhanced our understanding of the universe. And but there is no direct you can say direct implication on applications of this understanding, right? So but this is very important. This is a Bohr quadrant, and then this is Edison quadrant. So Edison was a scientist, or you can say he was an entrepreneur also, who was more driven by using the research or the know-how that he had access to for the benefit of society or for applied research. He wanted to apply that knowledge in actual, you can say, inventions. So he was not worried about. So this type of scientists are usually not worried about the phenomena. They may not know the phenomena behind their application very deeply, but they can very efficiently apply that phenomena for the benefit of society to make some inventions that are beneficial for us. So these are drastically opposite quadrants, but there is one Pasteur quadrant, which is a hybrid of these two quadrants. We know that Pasteur has done a lot of basic research, and he has discovered, I think, penicillin, I do not remember. But at the same time, he has also discovered a vaccine for rabies virus. So his research was both the basic pure basic research as well as application or use inspired basic research, you can say. So this is the ideal quadrant, but it is not possible for everybody to do this kind of research where the scientist is well versed with the basic of that phenomena, as well as he can use that for the benefit of society. There are very few people who can do this, but we should strive to do this kind of research. Then this is the fourth quadrant. That professor has not named it, but there are people who call it like the science that goes nowhere, or this is a black quadrant. So mostly the incremental research that many of us, including me, we do. So which is like just good for publications, for high impact publications and all, but we don't know if actually we can use that for the benefit of society, or if that is viable commercially or industrially. We do it just to put the number of publications in our CV, right? A lot of people do that. That is called as incremental research. This is less desirable. But why I have told you all this battery invention? Because what John Goodenough and his colleagues who got Nobel Prize last year, what they have done was also an incremental research. Okay, so this is not entirely bad as long as our intentions are good. Our intention should be, it should not be based on flaws in the what already has been discovered. It should be with the intention to make it more viable for commercial deployment. Then incremental research is also not as bad as it has been considered. Okay, as I said, that the intention should be right. So this is the story of 4 quadrants of scientific research, which I generally tell the PhD students or the postgrad students while they come for internship or when they come for their PhD, that they should remember this, and they should not go behind the number of publications or go behind the impact factors and all. These are all what you can say non-significant. What is significant is that what you understood from your research and how you could apply it for the benefit of society. That should be the goal. Okay, well, all this that I could have told you because this was 1.5 hour lecture, so that's why I took a liberty to tell you so many things. I hope you would have liked it, and if you want to ask me something, you can ask. Thank you.
Thank you, ma'am. Thank you very much for a nice, informative talk. You started from the basic and led us to the application part. And you also discussed about the pros and cons of different types of battery, importance of batteries. So now this talk is open for questions. So dear participants, please feel free to write the question in the chat box. So I have some questions. So from the for the participant who are watching this short-term course on YouTube as well as in this Google Meet. So I will read some of the questions.
So at least we know in which quadrant we are working now.
No, ma'am said that okay, she is in the fourth quadrant, but I don't agree with her.
I am in the fourth. Which quadrant? I said we know where in which quadrant we are working.
I am trying to migrate to the third quadrant. slowly.
It was very nice, yeah.
Very nice talk, ma'am. Very nice, very informative. Ma'am, we have some questions. One from Kankana Bros. Okay. This asking that lithium-ion polymer battery, where it was mentioned about dry, gelled, or porous polymer electrolytes. And her question is why we use organogel as the polymer electrolyte for lithium-ion polymer battery? How efficient will it be?
Organogel.
Yes, ma'am. The question is why we use organogel as the polymer electrolyte for lithium-ion polymer battery, and how efficient will it be?
Actually, the gels like polyvinyl alcohol and all are used as gel electrolytes. They have certain kind of ionic mobility, but they are not actually the electrolytes. They are just what you can say matrix for the electrolyte. We use lithium salts as an electrolyte in that. Instead of dissolving them in organic solvent, we use polymers as a matrix so that it can become a solid state. That is the only, what you can say, their role in polymer electrolytes. I hope I have satisfied her.
Thank you, ma'am. I don't know, maybe they can say that, but okay, for me it's fine. Okay, so ma'am, another question is, lithium metal batteries have high energy density and also high mAh per gram, but why we use lithium ion batteries?
Why?
See, the question is lithium metal batteries has high energy density and also high milliamp per gram. But why we use lithium ion battery? I think he want to ask that, okay, instead of lithium metal, why we are using lithium ion battery?
Yeah, so I think I have explained that while explaining you the lithium batteries, because in case of lithium metal, what happened during charging and discharging, when lithium goes and intercalates with the anode, and then when it comes back, because this is reversible reaction, right? When it comes back, the lithium ion does not get deposited on the same place from where it is extracted. It just randomly gets deposited, and sometime it creates a nucleation, and then the second lithium ion get deposited on that lithium ion, and it forms a dendrite kind of structure, very spooky structures that can poke the separator. I have showed you the entire assembly of the cell, right? So in that, if the dendrite forms and it pokes the separator, then anode and cathode comes in contact with each other, and then the short circuit can happen. So that's why that battery is not safe, and that is how then lithium ion batteries are discovered, where LCO or lithium metal oxides are used as cathodes and graphite as an anode. So this dendrite issue has been countered in lithium ion batteries. So that is why only. I know that lithium metals have very high specific capacity, but because of the safety issues, we cannot use them as it is as anode. I didn't show you, but in fact, one of my students is working on that also, lithium metal anodes. So instead of using lithium metal foil as it is, she is using pre-lithiated carbons, where she will be depositing lithium metals in some porous host, carbon host, and then she is studying that by doing lithium plating and stripping, if dendrite forms or how many cycles it will take for dendrite formation and all. So she's getting quite good results. So she's trying to optimize the host chemistry to avoid this dendrite formation. So that kind of research is also going on, but lithium metal batteries are researched and then they stopped using them because of dendrite issue.
Okay, thank you, ma'am. Ma'am, there is another question. What is the efficiency of sodium-ion battery?
So I told you that sodium ion is little bigger than lithium ions. The chemistry and everything is same in case of sodium ion batteries, but because the ion is big, it cannot intercalate with graphite as such. So we need to use some hard carbons or disordered carbons as an anode, and then that's why the specific capacity is very less when we compare to lithium ion batteries. So suppose if graphite anode gives us around 375 of milliampere hour of specific capacity, then hard carbons with sodium ion intercalation, they can give up to 150 or 180 milliamp hour. But sodium is aggressively being researched because that is very good for our country, in context of our country, at least for stationary applications.
Yeah, ma'am. Okay, you touched a very important point that okay, for if we want to go to the lithium-ion battery, then we have to procure the lithium from China.
Yeah.
And in the same contest, some participants are asking that you propose that okay, we should use the recycling of the batteries. The question is, what is the percentage of recycling material in this battery?
Well, so I am not directly working on recycling. We are not doing recycling in our lab. There is a company called eParisara in Bangalore. They do this recycling of lithium batteries. They are providing me the black mass or the electrodes that they have extracted, anode and cathode black mass, and then I am evaluating them. Like we are doing all materials characterization to understand the purity of the sample, and then we are making coin cells from those recycled materials, and we are testing them for their second life. So I am really not aware how much percentage we can recycle from those materials. Probably there might be some people who are working on recycling, but I am really not aware about all these things.
Okay, ma'am. One another participant at YouTube is asking that okay, LCA of lithium-ion battery as per present scenario.
LCA.
What is LCA? I don't know, ma'am. What is LCA? So, okay, if anyone want to ask the question, they are free to ask one or two questions if they have not posted on the chat box. Ma'am, I have one question.
Yes, Kiran.
Ma'am, as you are working on this iron oxide, Fe2O3 or other oxide materials, so my question is how we can decide that we can use these such oxide materials as an electrode? Is there any set rule to use any oxide material as an electrode material?
Yes, so we have to first understand their electrochemical potentials versus lithium. If we are using it in lithium battery, we have to understand their electrochemical potential versus lithium, right? So then I have showed you one energy diagram with respect to electrolyte HOMO and LUMO. So based on that energy diagram, we can decide whether that oxide can be used as anode or whether it can be used as a cathode.
Okay, so basically we have to understand the chemistry rather than any other physical properties.
Physical properties are also important, but first to determine whether it is anode or cathode, their electrochemical potentials are very important. Okay, because the lower the electrochemical potential, we can use them as anode. Higher the electrochemical potential, we can use them as a cathode.
Okay, thank you, ma'am. I think, ma'am, someone want to ask the question. Dr. Aditya, I think you want to ask some question.
Yes. Good evening, ma'am. Ma'am, we are also working on sodium-ion batteries, and we have prepared few electrodes like Na2TiO7. So actually, we don't have the testing facility in our lab. So in this case, it is possible if we send a student to you or making some collaborative research.
Yes, definitely it is possible. I think I NIT, which NIT? In Odisha, there is one NIT, right, Kiran?
Right. I'm in Delhi and NCR.
Yes, ma'am.
No, yeah, that's what I'm saying, that people from some NITs, they send their student to my lab, and they generally in CSR labs, it's a little tricky. So you can send samples and you can send student for 8 days or maybe 15 days intermittently. I can take permission for 8 days or 15 days and they can come and work in my lab. We do that only. Right now, we are not allowing any outside students because of COVID. Even our own students are also not there in the lab. Only 2 students are working at this moment. So once this virus situation improves, you can definitely send your student, or you can send your samples also.
Yes, so I will text you in the email, and I will make plan with you.
Yes, sure.
Yes, thank you.
Ma'am, I have another doubt. Ma'am, I got through the session was excellent actually. So my doubt is that can you please explain about the energy levels of the electrolyte again? I meant that HOMO. I didn't get that actually. Can you please explain that again?
Okay, so HOMO is highest occupied molecular orbital of electrolyte, and LUMO is lowest unoccupied molecular orbital of electrolyte. So there are certain, so each molecular orbital has certain energy levels, right?
Yes.
So the electrochemical potential of in energy of that anode should be lower than the HOMO of the electrolyte, and for cathode it should be higher than the LUMO of the electrolyte. Otherwise, electrolyte will react. Yeah, otherwise electrolyte will react. It will either get reduced or it will get oxidized. So we need a stable electrolyte. We don't want electrolyte to get reduced or oxidized, right? That's why this energy diagram is important. Of course, this assumption is quite disputed, but this is generally accepted as of now in battery field. But some of the people they are saying that probably this is not entirely right, and we should consider the Gibbs free energy of anode and cathode reactions. But that is quite complex, and that is also disputed. But this is more what you can say widely accepted assumption of HOMO, LUMO, and electrochemical potentials.
Okay. I didn't get what they stood for. Okay, highest and lowest. Okay.
Yes.
Thank you very much.
Any more questions?
I think there are not any, I don't see any other question. So thank you so much, Manju, for your wonderful talk, and I see very good comments from the participants. So
thank you, Harleen. I'm happy to see you actually.
Yeah, hope we could meet in person.
Yeah, you come to Pune sometime.
Yeah.
Because we have, I think Roxy is also here. We can.
Okay.
Yeah, Roxy works in IMMT, na? So he's also in Pune. We can have another get together of all Kabli fellows.
Yes, definitely.
Yeah. I met Shubha. I had a talk in IT Kharagpur. That time I met Shubha. You remember Shubha Verma? Yeah. So she was also very happy to see.
Picture of some conference are there, and I mean, all are very active. All the participants there.
Yeah.
All very active.
Yeah.
Yeah, I think Kiran has some.
Kiran.
Yeah. He wants.
Hello, ma'am.
Yes, Kiran.
Ma'am, thank you very much. I had some network problem at last moment, so I told ma'am to handle the situation.
Okay.
And Halil ma'am is very supportive actually for everything, as he is taking a lot of care to the department, and her leadership, our department organize many courses, and ma'am, this is really very much helping and for the development of the department. So it's great that Halil ma'am is heading this department. Thank you, ma'am. Thank you very much for accepting our invitation. And it is, ma'am, due to you that we have a very good speaker in this whole event. So you proposed many speakers, and they kindly accept our request. So
yes,
thank you very much.
Amrish and Sagar Mitra are there. I can see their names. Yeah.
Yeah. Mustafa, actually, he is busy. So he said that, okay, there are some presentation of his student.
Okay.
So but he said that, okay, he will join some other time. Okay. Thank you, ma'am. Thank you very much for making our day so special. And I think all the participants enjoy your lecture. You can see the comments in the chat. So everyone appreciate. Thank you very much.
And we will visit Pune, Kiran, next time.
I will definitely.
We went to this PACS Indore lab, this year in February. We took our MSc students there.
Okay. Yeah, Kiran worked in Indore for a long time, right, Kiran?
Yeah, ma'am, for 6 years. And
So Harleen, I know Kiran when he was doing PhD in Bhopal University.
ma'am, not from the PhD, ma'am. That when I was doing master from
Acha,
2000
master कर
onward.
रहे थे क्या?
Yeah,
Okay.
from
So I was
2000
only
onward.
married to his sir, huh?
Yes, ma'am. Yes.
Yeah. So my husband was teaching him, Harleen.
Yeah. He was telling me yesterday. So he's also very good teacher. So I asked sir that, okay, would you like to join? Then sir said, no, from one family, one expert is fine. So, yeah.
Okay, you
nice
can
of you, ma'am.
definitely come, Kiran and
We will
Harleen.
definitely
Both of
come
you are
and
most welcome.
definitely we will collaborate with you for the internship of our MSc students. We will send some student as soon as this Corona episode get over, and we will definitely we will work together on some interesting program.
Sure, definitely.
Thank you, ma'am. Thank you so much.
Okay, bye. Bye,
Bye,
Harleen.
bye, ma'am. Bye, Harleen, ma'am.
Bye.
Bye, Manju, ma'am. Bye. Bye. So, dear participants, thank you very much for your patience. And this session was occupied with full strength of 100 people. And we are looking to accommodate more participants on our interactive session, not on the YouTube only. So I will share the link to all of you if we go to the another platform. Maybe from tomorrow onward we will go on Microsoft Teams. So where around 300 students can join and they can interact with the expert. So for the morning we are really very sorry. Thank you so much and have a great day ahead. See you tomorrow at 10:30. I will leave the meeting now.